It's an honor and a pleasure to be part of the 2021 Indian Brazilian webinar, jointly organized by IGS and the Brazilian Geotechnical Society. And also it's a pleasure to chair the last day of webinar together with Dr. Nilima Satyan from Bombay. The 2 days earlier showed how productive cooperative action between India and Brazil can be, in as much of our similarities or disparities that to some extent we cover over the last 2 days. And I'd like to introduce Dr. Nilima Satya, that will present our first speaker, Professor Mahendra Singh from Roorkee, and I will introduce the second speaker later on. Dr. Nilima, please.
Ma'am, you are muted.
I'm sorry. So, good morning and good evening, everyone. So I welcome you. It's my privilege to welcome you all for the last day of our first Indo-Brazilian Geotechnical webinar. And myself, Dr. Nitin, so presently committee member.
Ma'am, I'm sorry, ma'am.
Like Professor.
Ma'am, you're not audible enough, ma'am. Dr. Nilima.
Hello?
Yeah, you're not audible. Can you correct the audio? Ma'am, your pause. Yeah, I think you are back now, ma'am.
I'm sorry, I had a very fragile internet at home. So good evening and good morning, everyone. So welcome to the third day of our first Indo-Brazilian Geotechnical webinar. And myself, Dr. Nilima, Executive Committee member of Indian Geotechnical Society. And along with me, we have Professor S.K. Prasad, who will be handling this third day session. And we are also very happy to have Professor Negro with us from the Brazilian side. So today we have four talks, two from Indian experts and two from Brazilian experts on two very important topics. One is like rock engineering and underground structures, and second one is on geoenvironmental engineering. So in the first day, our first talk on infrastructure developments in India by Professor Sitaram, we have seen like there's so many challenging projects have been coming up or like underway or planned stage in the country. These are most of the constructions that through rock. They fall in the Himalayan region, which is very, very seismically active, and also most of the, it accounts for the highest number of landslides in the world. So highly fragile slopes, and these are all like, affected by seismic and also rainfall. The construction activity in these regions are very, very challenging. And it's for all of us, it's very proud that several of our IGS esteemed members are actively involved in these projects like China Bridge or Atal Tunnel, and many tunnels that are coming, which are total 63 kilometers of tunneling activities is on the way, is undergoing in the Himalayan region. So our first speaker, Professor Mahendra Singh, who is a presently professor at IIT Roorkee, will be delivering his talks. And the second topic is also very relevant in the present situations or the time, which deal with the ever-growing problems that are related to geoenvironmental aspects, because right now the current situations and the emerging environmental issues, they all call for sustainable solutions for, in the engineering problems with very, very minimal damage to the environment. So with this, I will be very glad, and I feel that this is my privilege to introduce our first speaker from the Indian side, Professor Mahendra Singh, and who is professor at the Department of Civil Engineering at IIT Roorkee. And he is also presently president of ISRM India, And he has done extensively. He did his undergraduate in civil engineering in 1983 and master's from IIT Kanpur in 1985, PhD from IIT Delhi in 1997. He has a very, very strong research interest in, especially in the areas of slopes, landslides, and engineering behavior of rock masses and underground structures. He guided almost like 10 students, and more than 55 MTech students have been guided under his leadership. And he also authored more than 110 papers in several reputed journals and conferences. So actually, he has a very extensive biodata, and he's also one of the executive member of Indian Geotechnical Society, and very actively involved in organizing several technical events. He is the one who is done a lot of things, and organizer for this LARAM India course, which happened in 2020. With the collaborations from Italy and Norway. So he's instrumental for this event, and he's also a convener for the subcommittee in the Indian Geotechnical Society for virtual university. So with this, I request Mahendra Singh sir to take over and start this lecture. Thank you so much.
Thank you, Professor Nilima and Professor Negro. So let me share my screen. Is it visible? Can anybody respond? Is it visible?
Yes, sir, it is visible.
It is visible.
Okay, so good morning and good evening to all of you, my dear friends and colleagues. It's nice to have this joint webinar, and it's a very good learning experience for all of us. I'm going to talk about the assessment of shear strength behavior of jointed rock masses. And I'll be touching some of the contributions which have been made by Indian researchers. I apologize that I will not be able to touch all of them. Some of them I'm touching, and I'm also giving some idea about the work which we are doing here. With your permission, sir, I would like to dedicate this talk to our esteemed researcher, Professor Bhavani Singh, who just passed away 1 month back. Professor Bhavani Singh was he was the leading personality in rock mechanics community here in India, and he has contributed a lot, and many of the things what he has suggested or contributed, I'm going to touch upon those also. So here is the content of my talk. I'll be just some introduction of my institute as well for the benefit of the Brazilian friends. And then I'll talk about the jointed rock and rock masses. We here in India, we do not offer a compulsory course for civil engineers. I'm from civil engineering background, so my talk will be mainly towards civil engineering. So at undergraduate level, we don't offer compulsory course for the rocks. So I'll be touching this difference between jointed rock, rock mass, and how it is different from soil. And then I'll come to the shear strength aspect. There I'm going to talk about the discontinuity shear strength, means along the discontinuity, how one can assess the shear strength, and then our contribution on rock mass strength. And I'm also going to touch some empirical approaches, which include the Indian contributions. So here is the map of our country for our Brazilian friends. So this is somewhere. So in this map, you can see this is a small state, Uttarakhand. So here it is the small state Uttarakhand to which we belong. And somewhere here in this Uttarakhand, we are Roorkee here. So, and this area, this entire area here, that is Himalayas, and lot of rock mechanics problems, rock mechanics issues are there. And it's there are so many projects and so many activities going on, as Dr. Nilima has told. This is my department where I work, Department of Civil Engineering at IIT Roorkee, and at the bottom you can see the lush green lawns of my institute. It's a very beautiful campus. We enjoy the life here in general, but these days lockdown has created problems. Anyway, we hope that many of you will be with us. A little bit more about our institute, which is known as IIT Roorkee. It was established in 1847 as the first engineering college in British Empire. And then in 1854, it was named as Thomson College of Civil Engineering. And then it became University of Roorkee just after the independence in 1949. And on 21st September 2001, then it was converted. It was through an act of parliament, it was converted to, it was changed, its status was changed to Indian Institute of Technology. And starting from this November, we will be celebrating our 175 year of existence of imparting the education. Friends, I'm an academician, and whatever I'm speaking is based on the experiments done in the lab. So just a few glimpses of our laboratory. You can see here on the left-hand side, triaxial testing machine for rocks. So we can go up to 70 MPa confining pressure. Then we also have a very good polyaxial testing machine. Professor Samadhya, who is the chairman, the IGS president here, he was instrumental in bringing this equipment. So we have these facilities. Another very unique facility is this large site direct shear test, where this height is 1 meter and you can have a sample of 75 centimeter by 75 centimeter by 1 meter size, especially for soil boulder matrix. Then we fabricate some small setups as per our requirements. So for example, this is the setup for a bearing capacity PSD problem. Here, this is the rock mass you can see, and the small tunnel we had created and studied the behavior of rocks and so on. So, and here is a small rock mass under direct shear test. So these are the kinds of the things which we do at our place. Now, as coming back to the topic, as already discussed, there are a lot of infrastructural developmental activities taking place in Himalayas. You have heard to our very first lecture, and there are, whenever these activities are there, rocks are there. So whether it is a slope problem, whether it is a big foundation problem, or it is underground excavation problem. So everywhere there is a lot of input which goes from rock mechanics. And as I told you, I'm an academician. So based on the work in the lab, we are working on these kinds of the topics on the strength behavior of rock masses. When we talk about the rocks, they are never intact, they are fractured, and you can see the fractures there. You can see these planes of weaknesses. And what they do is they make the rock anisotropic, they make it jointed, they make it incompetent also. They are much more deformable as compared to what is called as intact rock. Intact rock means the piece of the substance which is free from any discontinuity. So this rock material which is existing in between the discontinuities is rock material, intact rock. And the overall behavior is then a complex behavior. So we have slope problems, whether you have a powerhouse, etc., etc. So the rocks are invariably jointed. And when it comes to the solving the problem of any geotechnical engineering, we need rock mechanics inputs in addition to soil mechanics. Most of the times, we can treat soil to be isotropic, homogeneous, and maybe many a times continuous also. But same is not the case with rock. It has, as I told you, the planes of weaknesses, which we call as joints. And the rock mass is very heterogeneous. It's a discontinuum. Failure mechanism is very complex. If you look at the photograph at the right-hand side, you can see there is a very prominent discontinuity which is going on like this. So this is going to play an important role if I consider the sliding of this entire mass. So in this direction also there are fractures, but the kinematically it is going to move in this direction as depending on the field situation. And my area is shear strength behavior of these kinds of the rock masses. So it's a complex, and complexity is because there is very high non-linearity in strength behavior. When I say tau in terms of shear strength or in terms of major principal stress at the time of failure, it behaves non-linearly with confinement, and moreover, it is anisotropic also. So here it is a classic figure which is always fascinates me, the work done by Ladani and Archambault in the 70s. So when I say, just a minute please, I want to move this. So the failure in the case of the rocks can take place along a joint plane. Anil, Nitin, how I move this top portion? It's coming on this.
So you just lift it at the side, or it's fine. We can see it completely.
You can see it completely.
Yeah, it is completely visible to us.
Okay. So what's going to happen in the field that there may be a discontinuity failure. Discontinuity means, say, for example, there was a wedge here, and this is a plane of weakness, joint plane, and the entire wedge moved into it. So there it is the shear strength of the discontinuity which plays a role. So when we analyze these kinds of the problem, we have to know that shear strength of the discontinuity. And on the left-hand side, this diagram, I just wanted to show you that the phi of the joint plane, you can may be much higher than the phi of the intact rock. This particular diagram, this is the failure envelope for the intact rock, and it is for the joint, which is I have taken this diagram from Ladani and Archambault, and you can see the gradient of this line as compared to this line is very high. So when the normal stresses are low, in the low normal stress range, there is sliding along the joint plane, there is translation, and there is a lot of dilation, and because of that, you have very high phi value. Whereas when you go to the higher stress level, what happens is that the roughness, the asperities, the angularities, they are sheared, dilation is suppressed, and the frictional becomes higher than the fracture strength, means the material starts getting sheared, and as a result, dilation is also low, and you get a very low phi value. So we have to take into account these issues. Similarly, if it is a rock mass which is failing, again from the same work I'm quoting it, when the rock mass is failing, rock mass is it has the blocks which are separated by discontinuities. So the blocks can fail, the blocks can rotate, the blocks can shear. So all kinds of these things can happen. And here also at low normal stress level, here again, what you find is quite high dilation in the low normal stress range, and that dilation is suppressed at higher normal stress range, and you have a non-linear kind of the shear strength behavior. So when we, these are the photographs from our lab where we tested the rock mass under very low normal condition, and there is a complex mechanism. So when we talk about the shear strength, so then it is a failure mode dependent phenomena. We have to consider what kind of the failure mechanism is there. So I divide the shear strength of jointed rocks into two categories. One is discontinuity shear strength, and second one is rock mass shear strength. So when I talk about the discontinuity, so it is the shear strength at along the joint plane, and here, as I discussed, at low normal stress, the sliding will be dominating. At higher normal stress, shearing of the intact material will become dominating. Similarly, in case of the rock mass, when I say rock mass, it is a large assemblage of intact rock blocks which are separated by discontinuities, and the potential failure plane in this case may lie partly along the discontinuity surfaces or partly through the intact rock. As a result, at the time of failure, the blocks may slide, they may translate, they may rotate, they may split, they may shear. So there is a complex kind of the mechanism, and also the behavior may be isotropic or it may be anisotropic. So these are the two basic categories or the classes of the shear strength which I generally use to look at this particular aspect. Now, coming to the first category of this shear strength, I'm not covering much because I'll be focusing more on the rock mass shear strength, but just to give you some idea, the most popular or most widely used equation is the same which we use in soil mechanics, the linear Coulomb equation. And if you look at the tests here, let us do some tests on the rock joint, and these are the points. And what we do is we fit a straight line, and then we use this tau equal to C plus sigma 10 phi equation. But actually, the behavior is something like this. So the behavior is actually like this. So here in this range, we are over predicting. So we have to have a non-linear model. So there are number of models available, and the basic, probably the first one was the patterns model, which is a bilinear model, and what it considers is initially a higher phi value with zero cohesion, and then after certain transition, then you have a straight line, another straight line equation, which has some intercept on the y-axis, and this is for, and then this value is residual friction angle. So these two equations can be used, but one has to know what is the transition and what are the parameters. As far as field applicability is concerned, there was very, as I told you, fundamental work done by Ladani and Archambault. And similarly, during the same time, Barton suggested his model, Barton's shear strength model, JRC-JCS model. It is called as JRC-JCS model. It is one of the most popular one, and I find it very convenient, especially in the field, and without any much experience, one can use it. So this equation is in terms of it. What it does, it takes the phi r value, residual value of the joint plane, and then adds some component which is coming from dilation. So JRC is the joint roughness coefficient. It is the measure of the initial roughness, and JCS is the joint wall compressive strength, which represents the strength of the discontinuity surface, and sigma n is the normal stress. So as sigma n increases, you can see this component is going to decrease, and we have the non-linear shear strength behavior. So this is very convenient, and the charts are available. One can compare these standard charts with the field and then get the GRC value. Now coming to the second category of the strength, which is the rock mass strength. So here also, Now here the failure is occurring through the entire rock mass. There will be some situations, say for example, if you are analyzing a very big, high slope or underground openings or foundation problems, then shear strength of the entire rock mass is required. And again, what happens is if you look at the test results, so these are the test from results from Hook, and these are results for intact rock, and you can see this is the resulting failure envelope, and you can see at a very high confining pressure, the phi value is almost becoming 0. At low confining pressure values, there is high phi value. So when we use the failure criteria to define, to express, to determine the strength of such materials, again, the most popular equation is conventional Mohr-Coulomb equation. And this can be written either in terms of sigma 1 at the time of failure as a function of sigma 3, or it can also be written in terms of tau at failure in terms of normal stress. So, and here I'm using these two terms, sigma C mass and C mass and phi mass. So this is the equation which is very popular. We can use it. And for the rock mass, now the question is how to get these C mass values and phi mass values. So generally, in the field, is it really possible that we can do the field testing? Is it possible, like in soil, we can test a specimen at different confining pressure, and then we can plot the envelope and we can find out C5 value? Is it possible here? The answer is no. So what we have to do is the shear strength parameters are not determined, but they are assessed. We have to assess them. So this is what is done. So there are many approaches. I have divided them into three, not approaches, rather three parts. So you can use the classification system. So in first case, I'm taking the rock mass rating, where a lot of contribution has been made by our Indian colleagues also. Then second classification is the Barton's Q rock mass quality index, which is very popularly used in India, and there is a lot of contribution on this also. So I'll just touch these two, and then I'll come to the simulation of the triaxial strength. Like if we are not able to do in the lab, we try to simulate it through what is called as failure criteria, and we are going to use nonlinear criteria. And there are Indian contributions, the first one and the last one, and also the most popular equation which is used at international level. I'll just touch upon that equation also. So first is rock mass rating. This is the classification approach. I'm not going in detail. There are few parameters which are supposed to be influencing the rock mass strength. These are the UCS of the rock, the uniaxial compressive strength, and 15%, maximum 15% weightage is allotted to this. Then there is another term, RQD. I hope many of you will be familiar with this term. It gives us the rock quality designation. It gives us the idea about the fracturing extent. So what is done is you take all the cores which are more than 10 centimeter length, add them, and find out this core recovery, modified core recovery, that is called as RQD. So 20% weightage is attached to this. Then spacing of discontinuities is very important. So 20% weightage is given to this spacing of discontinuities. If the discontinuities are closely spaced, we expect it is much more deteriorated quality. If the spacing is wide, then you are going to have larger blocks, and the strength is, or modulus also are supposed to be high. Then condition of discontinuities, whether they are rough, they are planar, and so on. So 30% weightage is for that. And also some percent weightage is given to groundwater condition also. So these ratings are given, and then some penalty is imposed because the discontinuities are going to have some orientation, and depending on the structure, the penalty is imposed. Say, for example, if it is a tunnel, minimum penalty is given. If it is a slope, then maximum penalty is given because it is going to be affected. There is no constraint condition. Slope is going to be affected by the orientation adversely, and the foundations are somewhere in between them. So RMR can be obtained, and it can be used to obtain the shear strength parameters. So these are the values which were given by Bienasky. And then our Indian researchers, they did a lot of work here. They applied them to some case studies, and then they found that these values were underestimating the shear strength parameters, and they have suggested these kinds of the charts, and the equations are also available, which I'm not presenting here. So this way, the contributions has gone into this aspect. Similarly, there is another system which is known as Rock Mass Quality Index. It was proposed by Barton et al. And the Q is calculated as RQD upon JN, JR upon J, JW upon SRF, where JN is joint set number, JR is joint roughness number, JA is joint alteration, and SRF is stress reduction factor. So our people here, especially Professor Bhavani Singh and his group, and there were scientists from SIMFER, Dr. R.K. Goyal and other people, they have worked a lot on this application of this, and they have come out with these empirical expressions which can be used to define the shear strength parameters. Coming to the simulation, like we do in the lab, what we do triaxial tests at different confining pressures, and then we fit an equation, and this is the condition which is going to be there. Now we do it numerically also. So it is done in the form of what is called as strength criteria. So strength criteria is an expression which gives you how the strength varies when the confining pressure is changed. So most popular equation which is known worldwide is Hooke-Brown, and at Indian level, a lot of work has been done at IIT Delhi, and we have also done work at IIT Roorkee. Please note, I am talking about the institutions or the work related to civil engineering projects. So a lot of work in mining, etc. is also going on. I'm not touching that. So for heavily jointed isotropic rock masses, the Hooke-Brown equation is given as this, and where in the field, the geological strength index is obtained, and using this geological strength index and the parameters of the failure criterion can be obtained, and one can apply this particular approach. And here it is the chart from Hooke-Brown for getting the GSI. It depends on the structure of the rock mass. So here it is going deteriorating in this direction, and the decreasing surface quality based on that GSI is used. And then one can use it in the equation, and for different sigma 3 values, one can find out sigma 1 and then simulate the results. This equation is applicable for isotropic rock masses. At IIT Delhi, the work started in 1980s, where a lot of experimental work done by the group which was led by Professor Ramurthy and later on Dr. K.S. Rao. So they did a lot of experimentation on model rocks and natural rocks. And finally, this kind of the thing they obtained, they plotted. So on y-axis, they put sigma 1 minus sigma 3 upon 3, and x-axis, they put sigma c upon sigma 3. And very good correlations were obtained. Later on, tensile strength also brought into picture. And this is the equation which was developed at IIT Delhi. And these are the parameters of the strength criterion. And they have suggested the values for different rocks, what are the different values one can obtain. Similarly, now when this was for intact rock, then they started working for the jointed rocks also. So a lot of testing was done in 90s on the jointed specimens, and especially the specimens were cylindrical specimens. So some of them are shown here. So they took one joint and then they kept increasing the number of joints. Also, they kept changing the roughness. They also kept changing the orientation. So all those parameters they have changed and did a lot of testing. And again, they found out, they came out with the criterion for their, this is the equation which they have proposed for jointed rocks. So here on the left hand side, you have sigma 1 minus sigma 3 upon 3, sigma 3, and right hand side, you have these criterion parameters, and sigma Cj is the jointed rock UCS. So this is the UCS. And here is the plot. You can see sigma C upon sigma 3 on the x-axis, on y-axis this value, and this kind of the linear relationship they got. And then they obtained these parameters, phi, alpha j and bj. They also did a lot of testing for that, and they found that they were very well correlated with the sigmas, this ratio, this UCS upon UCS of the jointed upon UCS of the intact rock. So this equation was proposed by them, and sigma Cj is an input for their work. And because all these parameters, alpha j, as well as this parameter and this parameter, they are function of this UCS. So then they did a lot of testing on different orientations, different frequency under UCS condition. And what they found was that these are the three most important parameters which affect the UCS of the rock. One is joint frequency. So maybe the most influencing parameters what they described was joint frequency is one of them. If you have higher frequency of joint, the strength of the rock mass will be low. Then inclination was another parameter. So they developed a correlation to quantify what is the effect of a particular joint orientation. Say, for example, if the angle of the joint plane with the loading direction is 30 degree, this is almost 30 degree, then the influence of the joint orientation is maximum. And third parameter which they found very important was joint strength. And by clubbing them, they came out with a factor which they called as joint factor, and it is a weakness coefficient. And if you plot the joint factor here on x-axis and the strength on y-axis, the strength goes decreasing like this. So based on this expression, they gave this relationship to get the strength of the jointed rock. Later on, when I was doing PhD at IIT Delhi, we did tests on the rock mass specimens. It was a model rock. And then we also developed relationship between the joint factor and the strength. And also we suggested the charts. Coming to IIT Roorkee contribution in the strength criteria, what we have been working is we have used a concept which is called as critical state concept for rocks. It was proposed by Barton long back in 1976. And what he has proposed is that if you keep on increasing the confining pressure, and then if you look at the shear stress versus normal stress behavior, then there is a maximum value of shear strength up to which the strength can be increased. The strength cannot go up to infinity, so it has to the failure envelope has to become almost horizontal. So it has to have a zero gradient at a sufficiently high confining pressure. And this was the idea which we adopted. And what we did was we started with a simple Mohr-Coulomb equation, which is a linear equation which we use everywhere. So this is the linear equation. And from there, we subtracted a non-linear quantity, only a second degree quantity. And then we came out with this resulting strength in terms of sigma 1 minus sigma 3. And then we put the boundary condition that at a critical confining pressure, this gradient has to become 0. So that was as per the critical state concept. And putting that, then we did a lot of analysis. We collected the data for almost more than 1,200 rocks, and we did back analysis. And from their back analysis, we found that the critical confining pressure is approximately equal to the UCS of the rock. And based on that, we have suggested this equation for the nonlinear strength behavior of the intact rocks. And we suggested the expressions also to get the parameters. It has single parameter phi I0, which can be obtained using this small simple analysis. And this is the diagram from Barton, and you can see here when it goes like this, and this is the UCS circle, and this is the circle which corresponds to critical state. And surprisingly, the sigma C and sigma 3 for this particular point were very close to each other. So there was this criterion we had proposed. In fact, in 2019 ISRM at Brazil, we have presented one paper also where the idea was that there are at least 15 tallest mountains. There are 15 tallest mountains whose heights are ranging between 8 to 9 kilometers. The question is why all these heights, maximum heights are between this. Why this is not maximum than about 9 kilometers? So, and the possible answer can be in this critical state concept. There is a maximum limit. There is a limit to which the strength can be increased. Later on, we extended this concept to the jointed rock also. So the concept was simple now, that it starts from the jointed on sigma 3. If I take here, then the criterion has to start from the UCS of the jointed rock, and finally it merges with the intact rock. This that at very high confining pressure, jointed rock and intact rock are going to behave in the same way. This clue we got from Brown, and then again by using this concept we had derived equation for the jointed rock also, and we have given the expression in terms of the to get the criterion parameter. So here again we to use this criterion, we use this parameter sigma Cj. And the beauty of this particular equation is that you can apply it for the isotropic as well as anisotropic rocks. We have also suggested an equation which was published in 2005 based on the critical state concept. If there is no triaxial test data available on the intact rock, we can also based on the UCS, we can roughly assess the triaxial strength behavior of the jointed rocks. So now the question is, finally question is that this starting point in our equation, how to get this starting point. So one can use, there are a number of approaches. You can use the joint factor concept, you can use the classification, but we suggest that there is one approach we have suggested that is called as strength reduction factor. So as far as classification approaches are concerned, again, there are expressions available in terms of classifications to get the UCS of the rock mass. So one can use these expressions. Again, a lot of Indian experience has gone there. Here also you can have the rock mass strength from the RMR and other approaches. This is what we suggest that we call it from strength reduction factor. What we have observed from my PhD studies that if you start with on this Deer-Wheeler classification, if you start with the intact rock, then as the rock gets jointed, the points move on a straight line. So the rock moves like this. The idea is that if you talk about the modulus, on the y-axis we have the modulus, and on x-axis we have the strength. So as the strength decreases because of fracturing, the modulus also decreases. And there is a very good correlation between the strength reduction and modulus reduction. And this expression can be used in the field. What you can do is you can conduct some simple test in the field. Say, for example, we have done this, one can do the plate load test or uniaxial jacking test. And from there, you can get the modulus of deformation of the rock mass in the field. And once that rock mass modulus is available, so you can use it here. You can use it here. EI is the modulus of the intact rock. You can get it from the laboratory. Sigma CI is the UCS of the intact rock. Again, you can get it from the laboratory, and we can get the rock mass strength. So it gives us much more confidence, and we have used it for some of our projects. What we did was we did cyclic plate load tests, something like this here. Simple test, not very expensive, and we got the modulus values. Similarly, at some places we did very small drift we made, and then we applied load in this direction, and then by taking few cycles, you can have the idea about the rock mass modulus, and then from there you can get the, you can put it in the equation and get the strength of the rock mass. We have also used our equations to suggest the bearing capacity, especially for anisotropic rocks. And what we used is the Bell's approach. So what we do is we consider two elements here, just below the foundation and just outside the foundation. And at the time of failure, what happens is the foundation is applying load here. So this specimen is trying to fail. It pushes the another element. So this element also fails. And here for this element, the major principal stress will be in horizontal direction and minor principal stress will be in vertical direction. So we start with this element, we calculate the overburden, and then we can find out what is the anisotropic strength of this element to fail. And then this element is in equilibrium with the previous one. So for this element, sigma 3 for this will be equal to sigma 1 for the adjacent element. So we get sigma 3 for this. And once we get sigma 3 for this, we can find out what is sigma 1 at the time of failure for this. And that will be equal to the ultimate bearing capacity. And this was published in 2005. And we have suggested the charts also to get the bearing capacity. Finally, I'll just like to come to one more thing, which is called as squeezing potential. A lot of problems are there. And I'll just discuss few things. The contribution which has been made by Indians, especially again, I go back to the work by Professor Bhavani Singh, and you can see here on this diagram, he has plotted rock mass quality, and here the overburden. So overburden gives you the idea about the confinement, and then he gets a very good line of separation, and that defines the equation for squeezing and non-squeezing tunnels. So in advance, one can get the idea about the squeezing is going to occur or not. Later on, other researcher from Roorkee again, Dr. Goyal from SIMFR, he suggested another modified Q. In fact, in Q, if you calculate Q value, there is a parameter stress reduction factor, which is not easy to determine. So he took it 1, and in terms of now new Q he called as rock mass number, and then he also got this kind of the plot, and there is very good demarcation line between the different stages of squeezing. So this is the way a lot of work has been done on the squeezing potential also. Way back in 1984, Jethwa et al., they worked on what is called as strength-based approach, and based on the strength of the rock mass and overburden, they have defined the potential for the squeezing. We have used one approach which is called as strain-based approach. This was suggested by Iden. So this is based on the analogy between the stress-strain response of the rock in the laboratory. This is the laboratory specimen, and how it is compared with the strain around the tunnels. So based on that ratio, they have defined the squeezing potential. We used this this particular the concept, and we use the critical strain concept. Sakurai has observed that if the strain at the periphery of the tunnel or the periphery of the opening, they exceed certain value, then there are problems. And this certain value is called as critical strain. So if the strain at the boundary is exceeding some value, then there are the squeezing problems are going to occur. In general, this critical strain is taken as 1%. What we did based on our studies, we suggested that this critical strain should not be taken as 1%. Rather, it should depend on the properties of the jointed rock and rock mass there. We suggested an expression based on our work for this critical strain. And then we said that this critical strain should be compared with the actual strain which is occurring there at the periphery of the tunnel. Either you can obtain that through numerical modeling, or you can do the monitoring if it is under construction. So we can check that ratio, and based on that ratio, then we can suggest, or we can in advance we can quantify whether there is going to be any squeezing or not. So this is the kind of the stress strain curves which we got from our laboratory test results, and we got the elastic strain, which is the basis of this concept. And critical strain we defined as sigma Cj upon Ej. And as I told you that there is a straight line which is followed by the relationship between E and I. And we use this relationship, we use this particular gradient, and we came out with this expression. The critical strain can be obtained in terms of the UCS of the rock, the intact modulus of the rock, and jointed rock modulus. So this value, if you find out, you can roughly assess. It is only a rough assessment. You can roughly assess the critical strain, and this ETJ can be modeled, can be obtained in the field, or you can use some correlations. We have used the correlations in terms of Q to further modify this equation. We used this equation which was developed by Professor Bhavani Singh, and our own expression for relationship between E and sigma Cj. And this is one expression which we suggested for estimating the critical strain. So critical strain, now you can see it is expressed in terms of UCS of the intact rock. You can get Q in the field, you can get EI, intact rock modulus, and the unit weight. Unit weight is in gram per cc. So one can calculate this critical strain here. Also, we used Barton's correlation for ETJ, and we developed this expression. And both of these expressions give almost similar results. So here it is using sigma CI, means intact rock strength, and intact rock modulus and Q value. And then one can find out the ratio of the observed or expected strain with the critical strain. And then one can have different categories, and one can be prepared to tackle them in the field. We had applied it to several case studies available, and we found that it's working well. So finally, there is a lot of work which is being done or has been done on, there are different aspects of, for example, rock mass tunnel support interaction analysis, numerical modeling, under analysis of stress strain behavior of underground cavities, etc. And a lot of work has been done at IIT Delhi by Professor K.S. Rao. At IIT Bangalore, Professor Sitaram has already talked about it. At our institute, Professor M.N. Viladkar has done a lot of work on these aspects, though he has retired a few years back, but still very active. And our current president, Dr. Samadhya, who is a colleague of us here, he has worked on analysis of underground cavities and working on these issues. And there are other institutes, IIT Madras, Bombay, and other IITs and NITs. There are a lot of work is going on. Then there is a National Institute of Rock Mechanics in Karnataka. They do a lot of work on the rocks. And there are departments, as I told you, my focus is towards the civil engineering side. So I skipped mining and earth sciences. There are many institutes in our country which are working in this area. So for example, IIT BHU, ISM Dhanbad, IIT Kharagpur, and in our own department, in our own institute, Earth Science department is there. And then there are societies, for example, ISRM India National Group is there. Currently, I am the president, and there is Indian Society of Rock Mechanics and Tunneling Technology. So a lot of activities are going on. So finally, let me complete the concluding remark that strength behavior of jointed rock is a very complex thing, and it is a failure mode dependent. We have to assess the kind of the failure which is going to occur, and whether it is sliding, shearing of intake material, rotation, etc., etc. And the failures envelopes are very highly nonlinear. There is a strong curvature, and the extent of nonlinearity is very high at normal stress level. So if you are working on landslides problem, probably it is much more nonlinear than in a deep tunnel. And for discontinuity shear strength, the Barton's model we find very convenient. And for rock masses, if you have very big isotropic kind of the rock mass, Hook-Brown criterion can be used. And MMC, which is developed at Roorkee and at IIT Delhi, these equations take care of the anisotropy also. And the advantage of our equation is that the parameters which we use are based on the triaxial testing, which is required at a very low normal stress, low confining stress condition. So triaxial strength tests under high confining pressure are not required. So this is a very good advantage with our equation. And one input which we need is the UCS of the rock mass. For that, one can use, and there are many approaches. Classification approaches can be used, Q can be used, but my personal thinking is that some field testing should always be there. Solely relying on the classification approaches is not desirable. And if you do that deformability test, which I discussed, it gives us a fairly good idea, not accurate, but a fairly good idea, depending on the resources, depending on the time, we can do these kinds of the studies, and this modulus values we can correlate with the strength values, and we can find out the strength characteristics. Finally, in our country, uncertainty is a very inherent characteristic of any geological prediction. So it will never be possible to get all the data. So we I always suggest that we use more than one approaches, along with some field testing, and then based on the wisdom of the designer or the worker, one can use the values. So finally, I acknowledge whatever I have presented to my teachers, to my colleagues at Roorkee, and my students who have contributed a lot in developing, in understanding all these things. So with this, I hope I covered in time.
Almost just in time. Thank you. Thanks very much to Professor Mahendra Singh on his most comprehensive review of behavior of jointed rock masses, and for his very clear and very nice presentation. Thank you, Professor Mahendra. May I have Dr. Prasad to have a few words before we move into our second speak, please.
You're very right, Professor Negro. It was a very comprehensive coverage by Professor Mahendra Singh, wherein he talked about his research and the research by Indian experts in different areas. So there is a lot of scope for us to work more in this area. Somehow I feel majority of India is not very much keen on working in rock mechanics area, mainly because we have Rocky Mountains in the north, we have in the south, but then middle of India it's relatively less. But yes, so this can trigger more research, especially between India and Brazil. Thank you, Professor Mahendra Singh.
Thank you. We'll come later to the questions after we have our second speaker to this first part of our third day of our webinar. And this time, I'd like to introduce Professor Tarcísio Celestino, a dear schoolmate of mine, as a matter of fact. He graduated from the same school we attended together at the Polytechnic School in the University of São Paulo. We finished in 1972. Tarcísio got his Master of Science degree and his PhD in rock mechanics from the University of California at Berkeley. He's currently a professor of geotechnical engineering at the São Carlos Engineering School, also from the University of São Paulo. And he managed to be also head of the geotechnical engineering group of a very traditional consulting company in Brazil, Temag Engineering. Actually, Temag Engineering was founded by one of the founders of soil mechanics in Brazil, Professor Milton Vargas. Tarcísio is past president of the International Tunneling Association. His period he covered there was 2016 to 2019. He's also past vice president for South America of the International Society of Rock Mechanics. Last year, he was awarded the Zagi Prize, one of the most prestigious awards of the Brazilian Geotechnical Society, and we're very happy for that. Professor Celestino will be talking over a fairly novel and promising approach of acoustic emission in rock fracturing. I'm sure you would be delighted by his presentation. Professor Tarcísio, please take the lead. Are you there?
Yes, I am, Arsenio. Thank you very much for your kind introduction. And I think that your kind words are exactly due to the fact that we know each other. We have known each other for such a long time. And fortunately, we are so good friends. Thank you very much, Arsenio.
I'm pleased.
Let me share my screen, please. Can you see it?
It is coming.
Oh, sorry. It was not in the beginning. I apologize. Now it's right.
Perfect.
So, as Arsenio said, I will be talking about this technique of acoustic emission to understand the process of rock fracturing. But before that, I should first thank the invitation to be at this prestigious webinar. And I should thank Professor Schneid for the invitation, and should also congratulate both associations, the Indian and the Brazilian Geotechnical Societies, for this initiative, which is so good. I would say that shortcuts between associations, between groups like this, are going to bring a lot of benefit for both groups. And I do encourage that we repeat this in the future. An outline of my presentation, I will give an introduction to the topic, the motivation and the objectives which led us to develop this new method for interpretation of acoustic emission information. We were actually trying to obtain information for the fracturing process of different rock types, as I'm going to show the results which we obtained. We adopted different types of rock, a very interlocked kind of rock like a Monza granite and a limestone, a marble, sorry, which has many cleavage planes. But we stumbled into a lot of problems with the current algorithms for acoustic emission, so we decided to develop our own. So in order for that, before talking about the fracturing process, I have to give you to bother you with some theoretical aspects of source localization in acoustic emission, starting with the traditional algorithms and the clap wave, which is the algorithm which we developed. For that, I have to show you the experimental program and the test setup. We developed this in the laboratory based on diametral compression tests, the so-called Brazilian tests, because they are very useful tests for this type of work. After we developed a technique about 25 years ago of making these tests stable just by controlling the diametral displacement. And of course, I'm going to show you some results. And it's nice that when we find results from from a new technique like this, it's always good to have some proof, some indication that the results are correct. So looking at petrographic analysis, thin sections from petrographic analysis, it's always useful to find out whether or not we are on the correct track. So we are going to compare this 3D localization of acoustic emissions with petrographic sections. And by doing this, we can actually have some understanding about the cracking process and the cracking pattern in different types of rocks, and the distribution of P-wave velocities inside the specimen. This is a point which I stress. It's an important feature of our method, because usual algorithms actually adopt the P-wave velocity as an input and as a constant throughout the test. And I'm going to show that it's everything but constant. It varies a lot, and not only in time, but also in space, depending on the location of the specimen. So we'll have a clear picture about the spatial cracking process and the identification of damage zones inside the specimen. Finally, I will draw some conclusions. I should say that this technique so far has only been adopted in the laboratory, but it's also The concepts are also good for field applications, and we are in the process of using this for an underground mine in Chile, but I don't have field results yet to show you, only laboratory tests. I'm going to bother you for the benefit of those of you who are not familiar with acoustic emission, how it works. Every time that we load a rock specimen, whether in the field, whether in the laboratory, we are actually creating stress concentrations close to micro defects, which all rock masses have. We have just heard this very nice presentation by Professor Singh, and the influence of the rock mass strength it's exactly because of the defects, which are much larger in the field, but also in the laboratory. Even though we have an intact specimen, it has a lot of micro defects which create stress concentrations, and those stress concentrations lead to the progress, to the propagation of the cracks, and this propagation releases seismic energy. And if this release of energy can be detected by sensors, by acoustic emission sensors, which can be taken to a data acquisition system where it can be treated and interpreted. The basic information which we get, since these sensors are nothing but piezoelectric sensors, we have the signal consists of the variation of voltage with time, and we can do a lot with those signals with respect to the amplitude, to the frequency, and so on. As I said, we are using the so-called Brazilian tests, diametric compression tests, because they are very simple to perform and very controllable, if I can call this way. Since 1995, I think it was the first time that we published this idea of controlling the test, of going over the peak just by imposing with a servo mechanism the idea that the velocity of the diametral displacement perpendicular to the load should be constant. So we tell the servo mechanism, do whatever you want with the load, but as long as the velocity of the UX displacement is constant with time. And by doing this, we can, we published this in 1995. By doing this, we can the test becomes stable and we go over the peak. And we can obtain information both in macroscopic and microscopic scales with acoustic emission applied to studying the cracking propagation process. We can do two types of interpretation: the qualitative analysis, where we just obtain the acoustic emission parameters, and the quantitative analysis, which is the one which I will be showing to you, in which we show the acoustic emission source localization. We can do this based on waveforms and frequency domain analysis. Due to time limitations, I will not be talking about frequency domain analysis. And as I said, we can do this also based on the information which we get from petrographic analysis to check whether our localization procedure is going to the right direction. The petrographic analysis which we carried out, of course, started with intact specimens, and we also did a lot of thin sections in different tests at different stages of the load, so we can compare what we are getting from the petrographic analysis with the localization obtained from the acoustic emission process. By doing this, we can be sure that our localization of crack propagation is correct. Talking about the typical algorithms for acoustic emission, they adopt, as I said, a p-wave velocity, Vp, as an input information, which is constant throughout the test. And this is a very strong limitation of those algorithms we have found. And because, first of all, because that was that VP is obtained under intact conditions, and along a test, the damage changes a lot the propagation velocity. Those algorithms can also define cluster boxes for where the energy is released, and they do this usually in dimensionless terms of energy. It actually doesn't matter whether we use dimensionless or dimensional energy. In our algorithm, we decided to adopt dimensional energy just for simplicity, but that actually does not affect the quality of the algorithm, as, for example, as the other case which I mentioned, the velocity. Yes, this one affects a lot the quality of the results. Then there is a searching algorithm for the localization process. Typical algorithms adopt the simplex methods, but there are other techniques which are also adopted for minimizing the error of the localization. They also depend on a technique for determination of the P-wave arrival time. The most frequently adopted technique is the first threshold crossing. I'm going to show you, but as soon as the intensity of the signal goes beyond this threshold, this is determined as the time of arrival. And this is a very crude procedure which introduces a lot of errors, but there are even typical algorithms have also adopted other techniques. Well, we found out that some improvements were needed for these algorithms, and this is what led us to develop this new algorithm, in which not only the coordinates of the source, the coordinates x0, y0, z0 in space of the source of seismic energy release are unknowns, but also VP is an unknown. And there is no problem in adopting VP as an unknown. We just need another equation, but as long as we have enough sensors, there is no problem in adopting VP. This was an idea which I found to be very useful, because now instead of adopting this as an input value, we measure it. It's much more realistic. We adopt the absolute energy in attojoules, but as I said, this is not an improvement. It's just a matter of convenience. We adopt a more efficient algorithm for searching the minimum of the error, as I'm going to show to you, with an iterative process for the localization. And another important improvement is that we now use two coupled criteria. We use the threshold criterion. Let me put the pointer here, sorry. We use the threshold criteria coupled with the pattern of the signal. There is a different pattern for noise and signal. So we first identify if this pattern has changed, and then we check the threshold as well. And this came out to be a very efficient way of determining the P-wave arrival time, with much lower error, as I'm going to show to you, orders of magnitude lower than the usual algorithms. This is the so-called clap wave initials for crack location by acoustic emission with P-wave velocity determination. We know that we can never determine the time that it takes for the signal to leave the source and reach one sensor. But we can do this by difference, adopting the concept of a trigger sensor. The first sensor to detect the signal is the so-called trigger sensor. And from this time on, we start our stopwatch. And when the signal reaches the second sensor, we can measure this delta T1. When it reaches the third sensor, we can measure delta T2, delta T3, 4, 5, depending on the number of sensors which we have. So we have this observed delta T from the time that the first sensor, the so-called trigger sensor, has been hit by the signal. We have we want to know the coordinates of the source, x0, y0, z0, which are our unknowns. We know the coordinates of each sensor, and we know the coordinates of the trigger sensor, which was the first one to receive the signal. And the delta t calculated is just the difference between the radial distance from the source to the ith sensor minus the distance from the source to the trigger sensor divided by Vp, the P-wave velocity, which is an unknown in our algorithm, which is an unknown instead of an input information. So this is our system of equations, which we solve with this iterative process, and our iterations search for the minimization of the error, which is the difference between the observed and the calculated delta t. Not only one error, but the mean error, which we minimize. The expression for the quadratic error is there, and that's what we minimize in our algorithm. Well, as I said, we adopted two very different types of rock: monzogranite, which is a very interlocked kind of rock, and marble, which is a monomineralic rock, which has a lot of cleavage planes, where we expect, and that's exactly what happens, where the energy will be released since the beginning of the loading process, different from monzogranite, which, as I'm going to show, it goes over the peak strength with very little damage. It's amazing. We would not expect this, but that's what happens. Interlocking is so efficient that the damage actually accumulates way after the peak. As I said, we are adopting diametral compression tests with 10-centimeter diameter specimens. This is the loading system. The LVDT to measure the diametral displacement, which is our variable to control, to make the test stable. We impose to the servo mechanism the idea that the velocity of this displacement is constant throughout the test. We actually also measure the displacement parallel to the load, but that's very difficult to measure on the specimen because it varies a lot. So we actually measure it from the loading jaws. We do not need that for this type of test, which I'm going to show you. But for other purposes, which we have been doing with the Brazilian test, by doing this, we can measure elastic constants. And because the displacement measured from the jaws concentrates deformations which come from the jaw, from the steel jaw, we actually take the solution of elastic contact, which is a very nice closed form solution. By doing this, we have two pieces of information, two unknowns. We can take the two elastic constants, but I'm not talking about this morning. The information which we take from the acoustic emission sensors is taken to amplifiers and then to a data acquisition system. This is a picture of a specimen with the three acoustic emission sensors on one side, 3 on the other side. We use a total of 6 sensors, the loading system and the data acquisition system. The type of curve which we get is like this. We go over the peak and the test is stable. And we may get up to I would say very large displacements, and the specimen is still intact. We can see a crack, but it did not break apart yet. We can take the specimen, it's still intact. And we also run tests with unload and reload cycles. That's very useful for measuring elastic constants, not so useful for the purpose of acoustic emission localization, as I'm going to show to you. So for the localization, we take profit of the information taken from these stretches A, B, C, and D, and F, and so on. As long as we are along the unload and reload cycles, there is no energy being released because of the Kaiser effect. So there is no acoustic emissions signals that we can obtain in the green stretches of this test. Well, taking, for example, the monzogranite, we know that this is the type of signal which we have after the peak, after the arrival, we have detected the arrival time of the P wave, the threshold technique. So I'm going to show you first the interpretation with the traditional the traditional algorithms. The threshold technique just says that as long as the signal goes above this threshold of amplitude, then we define this as the arrival time of the P wave. Of course, there are both positive and negative stretches of the P wave. The integral of the whole waveform is the energy for this event. And we can, now let's look at a real test in which we are going to follow what happens with the clusters of energy on the right-hand side. We are looking here at different stages of the test. We see that at the beginning of the test, the first cluster of energy release are at the contact of the specimen with the platen, because there are also always some irregularities which are crushed, if we call it this way, and they release energy, and we capture that. So this is actually useless for our cracking propagation interpretation, but nevertheless, that's information that we have to interpret. This is the scale for the energy in these clusters, which I'm going to show you. Since I'm talking of the traditional algorithms, energy here is given in dimensionless form. The gray color is the lowest energy scale. And so as we progress, we see that the clusters are increasing and that now there is some trend for clusters to be aligned along the future crack which will develop along the loaded diameter. But even though we are close to the peak, the energy released so far has been very limited, as you can see by the scale. So even now, we see a clear trend along the loaded diameter, but not yet a crack developed. So after we have gone through the peak, then this trend for the crack starts to become very clear. And now we even are changing the scale to the green boxes, which means higher energy released, and so on up to the end of the test. And now by the end of the test, we see that the energy released has become larger and concentrated very clearly along the loaded diameter where the crack develops. And we can follow here, we can see the energy released here, not only in the box, in these cluster boxes, but we can also see here on this graph, which not only do we see here load versus displacement, but also the cumulative energy in dimensionless form. And I call you the attention that this is 10 to the 6 power, whereas the next slide, which I'm going to show to you for the marble, it's an order of magnitude lower, to only go to 10 to the 5th power. So now looking at the same information for the marble, also at the very beginning, there is some energy released at the contact with the platens. That's natural. But now we see that very soon, even way before the peak, we already have this pattern of the clusters of released energy already indicating a region which will be the crack, the future crack along the loaded diameter, much sooner than what happened with the monzogranite. And I call you the attention, as I mentioned before, that here we have 1 order of magnitude lower energy release, only 10 to the 5th power. So when we reach the peak, it's already clear that there is a stress energy concentration of energy release along clusters, along the loaded diameter. As soon as we go after the peak, it progresses very clearly. And looking at the energy release, the cumulative energy here, we see that when we reach peak, we already have something like 1/5, 1/6 of the total energy which will be released in the test, whereas for the Monza granite at the peak, this graph showed practically zero, almost no energy, very little as compared to the total at the end of the test. So now it's very clear that the crack is being developed, even though we reached this stage of the test and the specimen is still intact. We compared this type of information, as I said, with petrographic analysis, taking thin sections, many thin sections of many intact specimens, many thin sections of specimens loaded at 70% of the peak and so on. Of course, we cannot stop the test, take a thin section and go back with the same specimen, because taking the thin sections is a destructive technique. But by doing this many times, we can have a pattern, a reliable pattern, I would say. This is the location of the thin sections which we obtained from the very center core of the specimen. And we took thin sections at these stages of test. At intact specimens, about 70%, 90% of the peak load, and at the end of the test. So let's take a look of what we obtained first with the Monza granite. And we see here this very tight microstructure, very interlocked. The grains of quartz, which are the stiffer ones, are those ones where the micro cracking process is going to start. I'm going to show when I show the first thin section after the load has started. In the marble, we know that there are the cleavage planes. It's a monomineralic rock, and cleavage planes in different directions, but also very packed kind of microstructure. As soon as here we have for the Monza granite, there was almost nothing at 70% that we could detect. At 90% of the peak load, we can already detect some cracks which have developed, which have started at quartz grains, which are the stiffest ones and the most brittle ones, if we call this way. And they also progress into other minerals like the biotite in this case here. It's very clear the penetration of the crack into the biotite, but initiated in the quartz grain, adjacent quartz grains. For the marble, looking at 70% load, we can already see some damage at 70% load, which we could see nothing at Monza granite. And we see this damage, which actually, it seems that some blocks limited by the cleavage planes have fallen off. And that's exactly what happens. They're missing here in these three thin section images. As the load progresses, 90% of the load, this damage is very clear. This area of missing blocks is very evident. And at the end of the test, the blue point, we see that this macro crack is very clearly developed. We see the same with the marble. And looking at the location of these of the acoustic emission location of the events at different stages, we are see here the load versus time. So we are looking at different stages of the load, and for each stage 1, 2, 3, we are going to follow 1, 2, 3, the three-dimensional location of acoustic emission events inside the specimen. and also looking at the scale of energy. So at stage 3, stage 4, we already see a trend for the formation of the crack. Stage 5, and if we rotate to get a better information about the three-dimensional position of these clusters, we get an indication about the future crack which is going to be formed. Now, looking at what happens with the marble, we see that with the marble, the clusters start to develop much sooner than they did with Monzo granite. That was, we already knew that from the previous information. So following the curve, we are past the peak now, but the damage accumulated is already very significant. And by rotating, we can have a better picture about the location, three-dimensional location. So now at stage 6, 7, approaching the end of the test, we see very clearly this crack along the loaded diameter. With respect to the mean error of minimization of the arrival time, with the clap wave algorithm, we see that the mode, this is a histogram of errors of different events, and we see that the mode is in the range of 10 to the minus 20 seconds. Very, very small error. The error being the difference between the observed and the calculated delta time. Here we are looking at the average error, the mean error, which is just the mean of the absolute errors of each event. Whereas if we look at the error obtained with traditional algorithms, it's orders of magnitude higher. The mode here is of the order of magnitude of 10 to the minus 6, whereas with clap wave it was 10 to the minus 20. So it's much better, the algorithm, as I said, as I had mentioned to you. Taking a zoom look at these peaks, we see here 10 to the minus 20 is the mode. Here, something like maybe 6, 7 times 10 to the minus 7 is the mode with the traditional algorithms. So one could say, well, it's just a matter of the propagation velocity. The answer is no, because the average for that test, the average velocity determined with the clap wave was 5.9 thousand meters per second. And if we impose different velocities with traditional algorithms, even so the error is much higher. So it's the overall algorithms which is much better. It's not just a matter of the velocity. And that's true for the mean error, also for the standard deviation of the error. The influence of the velocity it's not the only variable which influences the precision. The VP value is actually the result of an integral of the velocity which the signal takes to go from the source to the sensor. And it goes through different regions of the specimen with different degrees of damage. We are now going to take a look at velocities, average velocities, which were obtained from signals at different locations of the specimen. So this is the scale for velocities. And looking at what happens at different stages of the test, we see here that we start receiving signals from the contact between the specimen and the platen, stage 1, and this is with a velocity in the range of 2,000 to 3,000 meters per second at 50% of the load. At 70% of the load, we already start to have some trend for the major crack, which is going to start to develop. And we see that here we have this yellow point indicating lower velocity, indicating that this is already a region which is suffering from damage. The higher the damage, the lower the velocity. So as we progress, we see this trend for lower velocity at the center, which is, we know, the most damaged zone, and different velocities along different locations along the test. Just for comparison, the VP at intact specimens was 4.6 thousand meters per second, whereas here we have velocities ranging from all the way from 2 to almost 8,000 meters per second, depending on the location of the source. Looking along the diameter with a different angle. And when we look at the specimen, this is what we get from acoustic emission. And at the end of the specimen, we actually see a crack here. This is looking at one of the faces where sensors 1, 2, and 3 were installed. The crack is there, and if we look with a zoom, we very clearly see this crack, which has developed, but as I said, the specimen still intact. Looking at the other face, the face where sensors 4, 5, 6 were installed, it's not so clear, the crack, as it was in the previous phase, but nevertheless, it's there. When we look with zoom. What we can also see is that depending on the region where the events have been detected, the velocities are different. There is a pattern of different velocities at the contact zone, at the center core, and at the faces of the specimen, and even at the external boundaries. This was also surprising, but when we realize that there is a crack developing along this diameter, we can understand that there is a kind of bending mechanism in each one of these so-called half moons of the cracked specimen, which will lead to this bending, leading to some tensile stresses at the outer boundaries of these tests. So let's look at the difference in velocities at these different regions. At the contact zone, the velocities are high, are in the range of 5,000 meters per second. And just to remind you that the intact velocity of the intact specimen was 4.6 thousand meters per second. Here is the accumulated energy, and we see that because of heterogeneities in the specimen, they do not, at the upper and lower contact zones, the graphs are different because of heterogeneities of the specimen. That's actually nice to know. At the very center core, that's where we have the lowest velocity, because that's the region where we have the highest damage, the highest degree of damage. So here the velocity is in the range of only 1,000 meters per second. And this is what we get with respect to the progress of the accumulated energy. At the external core, at the faces of the specimen, we have this velocity also with a high value in the range of 6,000 meters per second. And why that? Because if we think that for the signal to come from this face to the sensors, they may go across regions which are damage-free. So that's why the velocity is so high at those locations. And again, the heterogeneity showing different energy accumulated at the two different faces. In the highest velocities of all, we get at the outer boundaries of the specimen. And it's clear that in this case, one could ask, how come the velocity can reach almost 10,000 if the intact specimen had only 4.6 thousand? Because now for the signal to travel from this point to a sensor which is here, it goes through a region which is under compression due to the load of the specimen. And this compression closes the micro cracks, the natural defects of the rock. So that's why there is an increase of the velocity because of the loading effect on the specimen. So the determination of VP provided important information These are the conclusions related to the distribution and evolution of damage and stiffness variability within the volume of the specimen. A non-homogeneous distribution of damage was observed, changing the characteristics of the specimen in comparison with the initial intact conditions. And that's why we say that the traditional algorithms which do not consider the damage and the variation of the velocity are very unrealistic. The use of a unique VP is very unrealistic, as I have just said. Further research is underway to determine the main reasons for this change of velocity, and there are a few possibilities. One is the nonlinearity of the velocity with respect to the energy released, that the velocity is influenced by the release of tensile stresses, that the velocity is also influenced by the increase due to the compressed zones. We are doing this with tomography, with voxels. This is actually the research of another student of mine, which is going on, Gabriel Bilesk. We don't have results of that to show yet, but so far the results are promising. So I should thank Patricia Rodrigues, my student who carried out this research very efficiently. FAPESP, the research funding agency for the state of São Paulo, for having provided funds for the acoustic emission device, and CONICIT, the Research Council of Chile, which paid for a scholarship for Patricia Rodrigues, who is a professor in Chile, during her stay in Brazil. Thank you very much.
Thank you very much, Professor Celestino. Excellent presentation. And very exhaustively you covered entire thing, principle, testing procedure, analysis using this acoustic emission technique. Very, very nice. And so I think Professor Negro, you can let me know, there have been a couple of questions to Professor Mahendra Singh.
Yes.
I have still not received questions to Professor Celestino yet. So can we start with questions to Professor Mahendra Singh?
Yes, by all means. I did receive one question to Professor Tarcísio, and I'll follow you, please.
Okay. So, there have been many compliments to both the speakers. And let me just take the questions to Professor Mahendra Singh. Okay, this is from one Mr. Satish Kumar. Can highly weathered rock or completely weathered rock be considered as rock mass? And rock mechanics equation, can it be applied in highly weathered rock or completely weathered rock for calculation of bearing capacity? Professor Mahendra Singh, please.
It depends on the degree of weathering. In fact, if it is just like soil, then you have to use soil mechanics theories. But if it is somewhere between soil and rock, then we can use those theories with maybe if you look at the GSI by Hook, that goes to very disintegrated mass. But one has to decide depending on the degree of weathering. But if it is a rock, then we can use the theories. Means we can treat it isotropic, highly coming under the last category of GSI. So that can be used.
Thank you. This is a question from one Mr. Shiva Kumar. He has two queries. First one is the joint made by cut throughout the specimen thickness diametrically or only at certain depth from the surface?
I think he is talking about IIT Delhi work. So in fact, there are ways of creating joints. Generally, people try to chisel. They use a chisel, and just like you do in the Brazilian test, they create natural joints also in the specimens. Some people use some chemicals like polymers, and they make the replica of the joint, and then they use it. but IIT Delhi, they use the molds to create the standard types of the irregularities. So that is one way they have done it. So mostly for model materials.
I think, in continuation, he says, is joint surface considered to open or close?
They use persistent joints mainly persistent joints, not non-persistent joints. So it was going up to the depth and considered them to be perfectly matching, means not open joints. Some work has been done at open joints at Roorkee. Some with filled joints they did some work.
This is one other question from Mr. Srinivas Reddy. Why the factor of safety for rock mass is much, much higher compared to that of soil, of course.
Because of our low confidence, we don't have that much confidence. Still people means when we work for the projects, means it's the type of the confidence which you have in soil properties we still do not have. There's a lot of uncertainties, a lot of issues,
complexities involved,
and complexities in the behavior, and also testing. If you go for a project, maybe sometimes you get only a UCS and RQD, and maybe not UCS is also not available. So the confidence is less there, and because of its complex nature, the factor of safety is kept higher.
Thank you very much, Professor Mahendra Singh, for a perfect lecture, and then your answers to the queries. I now hand over to Professor Negro to take over the questions.
I have few questions that have been put forward to Professor Tarcísio Celestino. One of them is, if cleavage planes were not present in the marble sample, would the seismic energy be released at peak strength, likewise the granite? In other words, if there were no defects previously in the marble sample, would the response be similar to that observed for the granite?
Yes, absolutely right. I actually showed the results of these two very distinct rocks. But when we have a cleavage-free rock, like we have also run this test on the so-called Botucatu sandstone, which is a very, for those of you from India who are not familiar with it, it's a sandstone which has been affected by some further, if I could, by some further flow of liquid quartz. Sorry, the words are, I lost the words now. But anyway, it's a sandstone very crack-free. It's maybe the most crack-free rock which we have around, and this is exactly what we have. In other words, the more previously damaged is the specimen, the more energy is released before the peak, and the other way around, the opposite.
Thank you. There are a few other questions from Dr. Jayalakshmi. Are any noise filtering techniques used in the testing, sir?
Very nice question. One way or the other, I would say yes, but nevertheless, filters, if we think of physical filters, they are very important for the threshold algorithm. They are not so much important for our algorithm because we actually adopt this filter which is looking at the pattern. When we look at the pattern of the signal and the pattern of the noise, we are one way or the other leaving information which comes from the noise. So it's not a physical, but it's a conceptual, if we call it this way, filter. And from that point on, we don't care about, we just look at the signal. We don't care anymore about if the signal is affected by some noise. we don't care because the amplitude of the noise will be much lower than the amplitude of the signal itself. But you are right, that's very important for the threshold technique only. And that's why the threshold technique leads to so much larger errors, as I showed to you.
Thank you. There is another question from Mr. Shubhan Shayed. He wants to ask about source mechanics in acoustic emission and how seismic moment tensor is used for micromechanics analysis of rock.
I must admit that when we look at seismic tensors and so on, that's we are going into field applications and we have not gone through those points yet. We intend to, as I mentioned, we have not gone to field applications yet. So I'm afraid I'm not able to answer to this question at this stage of our work yet.
Jolly good. There is a final question here to Mr. Professor Celestino from Sashitan Slack. The size of the specimen is 100 millimeter diameter and 50 millimeter thick. Will its affect compression, between brackets, buckling, for the expression to calculate the stress 2p or /phi is not really well clear to me. The stress. Could you follow, Tarcísio?
Not really. Is he talking about buckling?
He was talking about.
I think you know the size is 100 mm diameter and 50 millimeter thickness. Therefore, you know the L by D ratio. Will it affect the compression?
That's a good point. As I have shown that that there is difference in what we see on one face with respect to the other face. And that could be due to buckling, even though these dimensions, we took those dimensions because they are the suggested dimensions by ISRM suggestions for the diametral compression test. So to be honest, I had never thought of buckling. I think that the specimen is not slender enough for any buckling to take place, but there are differences from one face to the other, which I tend to interpret as heterogeneity. It's very clear that we see the crack, we see with a naked eye that the crack develops on one face significantly before it develops on the other face.
Dr. Prasad, may I close this first half?
I think so. We are running late, therefore I think it is better. Yes.
Yeah, once again, thanks to Professor Celestino for his highly elaborated and elegant research presentation that exposed us to real insights of microscopic failure processing rocks using quite an accurate and novel laboratory process. We thank you very much for your presentation, and also to Professor Mahendra Singh for his comprehensive exposure on jointed mass behavior. Thank you.
Thank you very much, Arsenio. Thank you very much, Professor Prasad.
Thank you very much. Yeah, and then, you know, from the Indian Geotechnical Society side also, to both the professors, Professor Celestino and Professor Mahendra Singh, sincere thanks for your very active, you know, presentations, and we look forward to many
discussion
more like
as well. Do we have time for intermission, or shall we follow the tradition going straight ahead? We are lagging behind us.
I think we are lagging behind, so we shall just go with it.
We should move. Okay. We are serial workers.
Okay.
Jolly good.
So I think, as
Dr.
was
Singh is
already pointed out,
Yes.
There will be two presentations. So can I start, Professor Negro?
Yes, please.
Okay, there will be two presentations. One from India, Professor D.N. Singh, and the other one is from Brazil, Professor Palmiro. Well, Professor Negro, Professor D.N. Singh, Professor Palmiro, and all my good geotechnical friends from Brazil and India. Good morning to friends from Brazil. Good evening to friends from India. We are into the last session of the 3-day first Indo-Brazilian Geotechnical webinar being jointly organized by Indian Geotechnical Society and the Brazilian Association of Soil Mechanics and Engineering. I, S.K. Prasad, am proud to be associated with this very successful venture. The theme of the last session is geo-environmental engineering. Indian geotechnical engineers have made decent contribution in this area of geo-environmental engineering. In the recent past, several projects are being taken up in collaboration with the governments and industry as well. Looking at the present scenario of managing, or should I say, mismanaging our Mother Earth all over the globe, there is a need to expand the scope of research and innovation activities in this area of geo-environmental engineering. An active collaboration between the two countries, India and Brazil, among the researchers, professionals, and even administrators is the dream of Indian Geotechnical Society. There can be, some important topics in this area for collaboration. It could be on the waste management and utilization of mining waste, mining tailings, municipal solid wastes, dredged materials, construction and demolition waste, nuclear and radioactive waste, carbon sequestration and associated environmental hazards, natural hazards and climatic effects, instrumentation and modeling, environmental impact assessment and policy formulation. Well, to talk about Indian progress in the area of geo-environmental engineering, I'm proudly presenting my good friend and a very popular accomplished geotechnical engineer, Dr. Devendra Narayan Singh, who is a professor at the Department of Civil Engineering in Indian Institute of Technology, Bombay, Mumbai, in India. He is with IIT Bombay since 1994 and has had a very illustrious career as a teacher, researcher, consultant, and a motivator. Before joining IIT Bombay, he served Central Road Research Institute in New Delhi and Indian Institute of Technology in Kharagpur for short durations. He obtained his bachelor's, master's, and doctoral degrees all from IIT Kanpur in the years 1986, 89, and 1993, respectively. His teaching and research activities are in quite diversified areas of geotechnical engineering. So he has handled, subjects like soil mechanics, foundation engineering, environmental geotechnology, mechanics of unsaturated soils, soil characterization based on thermal and electrical properties, contaminant transport in porous media, mineralogical characterization, utilization and recycling of industrial waste, geotechnical centrifuge modeling, and many others. He has published 320 technical articles, out of which 232 are in the referred journals. He has supervised 40 doctoral dissertations. 6 of the students are working at present, and 35 master's theses. He has been successful in filing 33 patents, out of which 15 have already been granted, 1 from the United States. Apart from teaching and research, Dr. Singh has been very active in some of the prestigious business houses as an in-house instructor and retainer consultant. He has taken up sponsored projects from Baba Atomic Research Center, Indian Council of Agricultural Research, Department of Science and Technology, All India Council of Technical Education, and Atomic Energy Regulatory Board. With financial aids received from these organizations and a few others, he has established a state-of-art environmental geotechnology laboratory at IIT Bombay. Dr. Singh is the founder, editor-in-chief of Environmental Geotechnics, ICE Publishings, London, and he is in the editorial board of many journals of repute. He is a recipient of Young Teacher Award instituted by AICTE New Delhi, Best Paper Award for the year 2005, recipient of Excellent Contributions Award in 2008, recipient of John R. Booker Excellence Award in 2011, all from the International Association of Computer Methods and Advances in Geomechanics. He was also chairman of the 12th, IAC MEAG in Goa in the year 2008. He is a recipient of Richard Feynman Prize in 2014 for the best paper published in ICE Journal, Canadian Geotechnical Journal, Fredlund Award in 2019 for the paper with highest number of citations among all those published by the journal in previous 5 years. Dr. Singh is a fellow of Indian National Academy of Engineering, American Society of Civil Engineers, and Institution of Civil Engineers, London. I am proud to present Dr. D.N. Singh to the August gathering. Professor D.N. Singh, the platform is yours.
Thank you very much, Professor Prasad, Professor Negro, Indian Geotechnical Society, and of course ABM, for giving me this opportunity to speak out my philosophy this evening in India, and of course early morning in Brazil. Thank you very much for this opportunity. What I'm going to talk about is something very new, not much into the practice, I would say. People are trying to understand this subject and they are taking it up. So the topic which I have chosen is geoenvironmental engineering. I'm D.N. Singh, and these are my contact details. I have taken the liberty of extending this topic to sustainable development by using the concepts of geoenvironmental engineering. And I am trying to draw an analogy between India and Brazil by considering them as long lost twins. In the subsequent presentation, you will realize that I'll try to show how these two countries have been connected culturally, philosophically, politically, and geotechnically, and put together everything. I call it as, a comprehensive sustainability map for the world. So please allow me to use this word, long lost twins, which I am going to use quite frequently in my subject or the discussion. Well, I'm going to raise several questions where I'm struggling and where I would like to draw the attention of my Brazilian colleagues. And I would request them to educate us, because in India, geoenvironmental engineering is still in the stage of infancy. And I know that many of the Brazilian colleagues have done tremendous amount of work in this subject in the past few decades. So if you go into the philosophy of these twins, which I have used, you will find that football is a religion in both the countries. More than the God, we are aware of the names of Pele, Ronaldo, Ronaldinho, Rivaldo, and so on. I'm sure every kid knows in the country. And in fact, these are better known than the speaker, and for that matter, even the audience also. Incidentally, I don't know whether many of you are aware or not, both the countries respect beauty. And we have won 2 times the Miss Universe pageant. Sushmita Sen and Lara Datta from India in 1994 and 2000, and Ida Maria and Martha 1963 and 1968, before I was born even. Festivities occur with great fervor in both the nations. Brazilian Carnival is famous for this. And Samba is famous, and we have in India several occasions to celebrate and several occasions to greet each other, festivals. A lot of things are common. Both the countries have a reputation for beautiful and talented people coming from our film industry. So telenovelas in Brazil and Bollywood in India, they are at par with each other. Both the countries have a love for over-the-top drama TV series. Brazil's most popular TV show, in fact, is motivated by an Indian story, where the Brazilian actors have acted and dialogues are delivered in Portuguese and with seasoning of Hindi, which is the official language of India as a slang. We also share a heritage in terms of tribes. And these tribes are actually, they have their own shelter, they have their own lifestyle, and they live like their ancestors without changing much. Now, why I'm covering these topics over here is because I'm going to link it with the sustainable development, which happens to be the topic of the talk. So Amazonian tribes in Brazil and the tribals in the remote part of India, they are still into traditional lives. And like their ancestors, they indulge in hunting, arts, and food, clothing, and agriculture. I'm sure you must have come across this news, a very hot news in yesterday's Times of India, or maybe the TV channels across the world. What it says is that India and Brazil and the world is watching who will win this inflation challenge. And that is the situation which has been created because of the COVID-19. So this is where, again, we have a lot of relationship, a lot of correlation, and a lot of match of the political situation in both the countries. This is the link, and you will be surprised to know that India has also joined the league of these big 5 COVID nations, where we have US, Russia, UK, Brazil, and of course now in India, we have the situation. So there are a lot of things which are common. I'm just trying to derive that. To continue with the twinship, unfortunately, poverty is also prevailing in both the parts of the world, both the countries. Like any developing country, there are certain fraction of the population which lives in absolute poverty. And there are very good movies which have been made out of it, where the slums of the Bombay and the favelas of Sao Paulo and Rio have been depicted in the form of the Slumdog Millionaire, which is a very famous movie, and Fast and Furious 5, Rio. In fact, when I was a student, I was quite fascinated by the movie Blame It on Rio, and that was my first introduction to the Brazil, though I could never visit Brazil personally and physically. Unfortunately, crime and violence against women is also quite matching in both the countries. And this is a matter of great concern to everybody. Interesting thing is that to alleviate poverty and such type of petty crimes, the BRICS formation has occurred. And BRICS, I'm sure many of you are aware of, is the group of nations, 5 nations, where B stands for Brazil, R stands for Russia, I for India, C for China, and South Africa, S. And these nations in the form of the BRICS are doing a lot of work to alleviate the negativity from the world, I would say, which again leads to the sustainable development and prosperous development. Some of you, I'm sure, who are interested in the entrepreneurship related platforms, you will find there is a very good book written by several authors, Entrepreneurship in BRICS, and the platform which can be utilized. And incidentally, you will find that there is an interesting MOU signed on BRICS Women's Business Alliance. So BRICS is doing a lot of work. Now, having said this, I will shift my focus related to BRICS from socio-economical aspects to the technical aspects. So what BRICS does? If you look at the charter, there are few memorandum of understandings related to science and technology. And this science and technology cooperation is in the field of innovation, mostly. And the first thing which comes in the agenda is exchange of information on policy and program and promotion of innovation and technology. I think this is where both the nations have to work together to come out with the solutions so that the sustainable society can be developed. Food security and sustainable agriculture is becoming another issue where geotechnical engineers are playing a very important role in the realm of environmental geotechnology or environmental geotechnics, I sometimes call them. The climate change is an issue, and the natural disasters and the preparedness for this and how to mitigate this is also becoming a major issue. Some other topics which we can pick up from this list are water resources and pollution treatment. This is becoming a major issue in both the countries where the water bodies are getting contaminated, and the dire need is to depollute the water bodies. And later on, I'll talk about the sediments which are an integral part of the water bodies. We are poised to set up high-tech zones, science park and incubators to start startups for our younger generations. Technology transfer, science popularization is another important facet of these MOUs. Information and communication technology, which has become a very important part of modern day geotechnical engineering and geoenvironmental engineering because of the big data and the cloud computing, definitely the sensors, which the other colleague was talking about yesterday and of course today before this presentation, and linked with the communication technology. These are the tools for monitoring what's happening in the field. At the same time, there is a lot of emphasis on clean coal technology. Brazil is a mining major. I think this is where Brazil can really help India in coming out with good solutions related to the clean coal technology. We call it as a coal beneficiation. After the mining is over, how to beneficiate the coal so that the calorific value can be increased, ash content can be decreased, and the value of the coal becomes much more. We can call it as valorization of the coal itself. There's another emphasis which is of interest to today's geoenvironmentalist would be natural gas and non-conventional gases, particularly the methane gas, which is coming out from the seabeds and how to exploit it. And I will be touching upon these issues as well subsequently. Climate change, as I said, is a big issue. And there have been few workshops which have been organized in the past under the realm of BRICS, where the change, prevention, and mitigation of natural disasters in Brazil was discussed. Similar things should be done from the Indian side also. And I hope you'll realize the time has come when the geospatial technology and application for development in India becoming a very major issue. And to elaborate this, what is the overall picture of the geospatial technologies? Basically, you want to do the remote sensing, you want to adopt the best possible mapping and surveying techniques. So the role of geospatial technology would be in several domains, and particularly they can be applied to the Indian context, where we can talk about the agriculture, food scarcity and nutrition, and what I call it as a man-made soils, the artificially created soils, and land rejuvenation and the soil rejuvenation. These are the terms which we are using in the realm of environmental geotechnology. And this is what actually is the need of the hour. several resources of oil and gas, environmental management, forestry, and the public safety against the hazards and infrastructure is also the top agenda. There is a young forum for BRICS, which is also very active. So my whole idea of showing about the BRICS was, having been associated with the Department of Science and Technology of India, I am aware of that the BRICS is a very, very active system which is encouraging research through these 5 countries, and I have been a part of this scheme. Now, another interesting thing to deal with the COVID type of a situation, if you go to the website of Department of Science and Technology, that is the DST of India, you will find that very recently there was a meeting which has been concluded on the online platform on May 25th and May 26th, where the focus was emerging issues in biotechnology and biomedicine. Now, I'm sure some of you will be surprised that as a geoenvironmentalist or a geotechnical engineer, why I have brought in this discussion over here. You will be realizing that agrobiotechnology is the focus of geoenvironmental engineering, food and nutrition, as I said earlier. And this is where we have to play a very, very important role in getting, the vegetation not affected by the pollutants which are being discharged from different sources in the geoenvironment. Now, another thing is of our mutual interest would be pathogenic activities due to the COVID activities or the COVID virus. And this is where I am happy to share that the journal Environmental Geotechnics has taken some very proactive action during the COVID time. And these are the 3 editorial board members or associate editors from Brazil, Professor Maria Bosco, Professor Enio, who is going to speak just after me, and Professor Paulo Hemsi. So these are the 3 associate members which I have in the journal from Brazil. So this journal has also strengthened the ties between India and Brazil. We have come out with a themed issue on COVID. So if you click over here, then you will see that this is the volume 8.3 of May 2021. And this was a very unique exercise which was done by the prospective authors by bringing in several authors across the globe and penning down their concepts and ideas related to geotechnical and geoenvironmental engineering education during the pandemic, how to deal with this type of situation where most of the universities and the colleges are shut down and everybody is doing teaching and consulting or interaction using the virtual platforms. There's a second paper which has been written by my colleagues, is the Municipal Solid Waste Management under COVID-19 Challenges and Recommendations, where we talk about the pathogenic activities, how pathogenic activities migrate in the porous media. And these pathogenic activities are emanating from the landfills, including the microplastics and the nanoplastics, which are causing havoc to the geoenvironment. So what are the challenges and what are the recommendations? This is what the major theme of this manuscript or the publication is. We have also championed a paper on mass burial sites for safe and dignified disposal of the pandemic fatalities. And this talks about the special measures which should be taken under the pandemic type of a situation for the burial and dignified disposal of the carcass of the animals or the human beings and dead bodies and so on. So post-COVID-19, water and wastewater management has also become a very big issue. And how to protect public health and geoenvironment is the major theme of this issue. So my basic idea of showing these 5 papers which constitute the theme issue is that geoenvironmental engineering appears to be a panacea for solving the problems which are getting created because of these extraordinary circumstances which the entire world is facing. And one more paper which we have included in this theme issue is environmental geotechnics, challenges and opportunities in the post-COVID-19 world. So how the future would be, what measures should be taken to come out of the situation and move ahead. I'm aware of my colleagues from Brazil side who are very actively involved in the geoenvironmental engineering, and I have named some of them over here. And I wish that in days to come, we are going to collaborate much more to solve the issues related to sustainability. Now, let me pick up about the sustainability issue, which I wanted to talk about. So before I venture into that, it's a good idea to understand, apart from the socio-economical background of the two countries, what are the similar aspects which are related to geographical issues. And geographical issues would be leading to the geotechnical issues as well. So if you compare India and Brazil, what you'll find that biodiversity is common in both the countries. And biodiversity is also becoming a part of geoenvironmental engineering these days. The flora and fauna and how it influences the soil, how it gets influenced because of the soil types, the rock types, the groundwater types, the climatic conditions, and so on. And what another interesting thing which we have common in is the coastline, which is almost 7,000 plus kilometers for both the countries. And the natural resources where the Brazil has a very significant strength in terms of mining and in terms of handling the tailing ponds. We have heard the other day Paula Francesca talking about this, and Dr. Chitra talking about this. So bauxite, gold, iron ore, manganese, nickel, phosphates, hydro power, uranium, timber, petroleum are the main natural resources which we share. Natural hazards are also very common in both the countries, and the average rainfall is also matching incidentally. So if you consider these numbers, you will find that India is also full of the biodiversity hotspots. Forest cover is also another issue, and the coastline is similar, natural resources are similar, natural hazards are similar, and the average rainfall is also falling in the same range. So truly speaking, our geographical, geotechnical conditions are also quite similar. And another interesting thing is that both these countries have diversified soils and peats also. And peats are becoming a major issue. So restoration of peats, weatherability of peats, and the structures which are located on the peats, how to stop them from getting distressed because of, let us say, the weatherability of the material, because of the oxidation of the material, and so on. So these issues are becoming very, very important in both the countries. And not much significant work has been done in India so far as the weatherability and disintegration of the peats is concerned. So I wish that Indian researchers would learn from the Brazilian researchers who have done a lot of work in this area, how to restore peatlands. And this is a topic which is a very challenging topic in the realm of geoenvironmental engineering. We are coming out with one themed issue on peatland restoration also, which is being championed by Brendan O'Kelly from Trinity College. So if you continue this similarity comparison between the two countries, you will find that the major challenges which geoenvironmentalists are facing are listed over here. That is the land degradation of different types. It could be because of contamination, deforestation, which is leading to the landslides, polluted water, dust sediments, tailings and dams. As I said, Brazil has a very, very high experience and expertise in this area, and this is what we require to learn from Brazil. Hydro and renewable energy, wetland degradation. We have done a lot of work in India on this. Peats, oil spills. Sustainable waste management, both municipal solid waste and industrial byproducts, is the need of the hour. And this is where we should be working together. And this concept will also lead to the waste to energy concept. And why it is happening, everybody understands, because of the rapid urbanization. We are not able to control the urbanization. Sustainable waste management is becoming a very big question mark. Brazil has a lot of good experience of dealing with big municipal solid waste, their closure, their stabilization, and so on. Because Brazil happens to be a champion in geotextiles and geomembranes and their application and georeinforcement and so on. In India also, since long, researchers and academicians and the industries have been using it. But I think now the time has come when we should be using these materials for geoenvironmental applications. Forest fire is becoming a major issue, and we have to do something on this. It's not only the environmental hazard. What happens is after the forest fire, the soil gets degraded and vegetation becomes quite difficult. And this is where thermomechanical coupling, which nowadays people are talking about, some researchers in India have already started, and they are trying to see once the soil gets exposed to very high temperatures, what really happens. Droughts and floods is a perennial phenomenon. And of course, the climate change, which is affecting the entire world. So this is where we have to really sit down and do things together. Let me now bring into the concept of sustainable development and how sustainable development is linked with geoenvironmental engineering. United Nations has very recently, in 2015 September, has included 17 SDGs, we call them Sustainable Development Goals. And these sustainable goals have been created to alleviate the poverty, to bring everybody at par, so that nobody is left behind. And this is a new agenda, which is defining the holistic approach for attaining the sustainable development. So if you look at the list, these are the 17 SDG goals, which we are trying to achieve. With my limited knowledge of the subject, I started talking about that geoenvironmental engineering happens to be a panacea for solving the issues related to the sustainability. And then if I tick mark on the matrix, which is given over here, we can talk about the poverty alleviation by using the concepts of geoenvironmental engineering, because this is directly dealing with the societal effects. Whatever we study in geoenvironmental engineering touches upon the quality of life of the people, creating more waste to wealth. I mean, this is the mission which is going on in India through Government of India. We call it W2W, waste to wealth. So when you are creating waste to wealth, the poverty alleviation takes place. Of course, more nutrition, more nutritious soils, more less polluted soils, more vegetation, more yield, more crops, no hunger. Quality education, of course, is an agenda. And clean water and sanitation, I have already touched upon this. Then we have the affordable and clean energy. I'll be giving you some ideas about this. And then decent work and economic growth, which is also linked with the SDG. And of course, industry, innovation, and infrastructure. The major agenda in India right now is, and for that matter, even in Brazil, is how to utilize the waste which is coming out from different sectors of industry and the municipalities to create infrastructure, innovative infrastructure. Then sustainable cities and communities. And of course, proper utilization of the resources, responsible utilization of resources in the scientific manner. Paul was talking about several disasters and the failures to how to avoid them. Then, of course, the climate action and the life below water. This is also becoming a part of geoenvironmental engineering, where we talk about submarine, slopes, water, sediments, and how to do their cleanup, and how to utilize them, how to trace them, and how to create different type of infrastructural facilities. Life on land. So that was offshore. Now this is the onshore situation. And of course, the partnership work which we are trying to do through these seminars. So in short, quickly, if somebody asks me what is the philosophy of sustainable development, whatever we are taking out from the earth crust, if I can give it back into the earth, this is what the earth crust can be exploited in a way which is sustainable. So you can do mining, whatever ores are being generated, the ores can be processed. And when you are doing the processing of the ores, the mineral extraction can occur. And when the mineral extraction is being done, byproducts are being generated. Now, these byproducts are going to cause a problem. I call them as IBPs, industrial byproducts. And these products, unfortunately, they cannot be transported because of the cost associated with them. So they are simply lying over the place where they get generated. And it's becoming a point of debate that to whom they belong to, and who is responsible and who has the onus to come out of this situation. So handling, disposal, and storage, all of them are becoming a major issue. The more industrialization is taking place, the more exploitation of natural resources is occurring, and then we do not know how to use resources. We can only utilize them partially so far. However, I believe that there are several geoenvironmental applications where these industrial byproducts can be utilized so that we can complete the cycle of sustainable development. Now, the questions are, when you are talking about the geoenvironmental application, what best can be done? So answer is bulk utilization. I'll show you some examples where the bulk utilization of industrial byproducts is being done in the country, and similar projects we can take up together and we can execute them. So when you are talking about the bulk generation of the industrial byproducts, how to minimize the quantity, but then this becomes a process engineering. This, truly speaking, does not come into the domain of civil engineering or geoenvironmental engineering. But of course, if you can optimize the quantities, and if you can reduce the quantities of the byproducts which are generating because of the chemical processes or metallurgical processes, or because of pre-treatment, as I was talking about the coal beneficiation and so on, this is going to be something which is very, very innovative and futuristic. Just to showcase what we have done into this field so far, myself and my ex-students now who are very well placed in different parts of the country and abroad also, we have been spending most of the time understanding the geomaterials. When I say geomaterial, this could be soils, this could be rocks, it could be groundwater, it could be man-made materials also, which I call them as anthropogenic geomaterials. Biosolids is a good example. Municipal solid waste is a good example of this. All right. And then different type of sediments which are coming out of the ocean beds or the lake beds, because they are also anthropogenically created. You have dug out them from somewhere and then you are placing them on shore. So we have done studies related to soil contaminant interaction, where we have studied the sorption desorption characteristics, how contaminant transport takes place. This has been done for nuclear waste also. So we have been dealing with the toxic hazardous waste both. And then industrial byproducts, which I was talking about. We have talked about the fly ash, conversion into zeolites, bauxite residues, coal washery residues, slags, different types of PRBs, and then infrastructure development by using these waste. So this is a big question. This is where I think I would be requiring help from Brazil, my colleagues who have been champions in this subject, and we can work together. Municipal solid waste is a big question still. Design and development of sensors we have done, soil moisture, we have done impedance spectroscopy up to gigahertz range to detect the moisture content and the density and the presence of contaminants in the soil mass. We have talked about the piezoceramic elements also. We have used them quite extensively for non-intrusive soil testing and to detect their geomechanical response. Dredging and mining is something which we have been into, and as I said, the coastline matches for both the countries. So dredging and mining activity also appears to be a very good area where we can really collaborate. And of course, the recent fad is energy geotechnics, where we are dealing with the gas hydrates and multi-phase geomechanics, frozen soil geomechanics, because of the reason that in India, a certain part of our country are always snow-clad, and heat migration through geomaterials. And ultimately, the million-dollar question is, having done all these geometrical characterization, what is that you want to do? So once the geometrical characterization has been done, we want to utilize them for different applications. So as I was talking about my students who are placed in different parts of the country right now, they could be very good BRICS partners for our Brazilian colleagues. And this map shows how the franchise of environmental geotechnology or geoenvironmental engineering is spreading all over the country. And these are the potential partners whom I think we can approach to develop joint proposals under BRICS program, and we can start working together. Some examples which I was trying to show you about industrial byproducts. This is where I'm leading a mission at the national level, Indian level, known as Mission IBPs. And these are the IBPs, industrial byproducts, which we have used so far: coal ash, mine tailings, construction debris, red mud, and steel slags. And we have done some initial trials, both in the laboratory as well as in the field, to stabilize marine deposits. This is the typical example of the red mud, which comes out of the bauxite refineries, where the alumina is being refined. And my idea is to convert them into artificial soils, man-made soils, and so on. This is the geopolymerization of the waste by marrying different components of the waste together under different climatic conditions. You can geopolymerize them, and then we are using them for creating infrastructure. These type of trials are already going on in the country. And this is a very ambitious program, which has been cleared by Government of India very recently, about the mine backfilling by using the industrial byproducts and the municipal solid waste also. Now, the questions are related to the organic soils, as I said, peats and the municipal solid waste. We are not really in a very comfortable position as a nation. There are several heaps of municipal solid waste which are lying here and there, and these are creating a potential hazard in terms of fire, in terms of stability, in terms of leachates, in terms of seeping of contaminants, in terms of being a source of attracting birds, vultures, and so on, mosquitoes, whatever you may name it. The question is that how I can quickly decompose municipal solid waste to create more land, more space, more storage space in the existing landfills, because the problems are very well understood. So there's a very strong contingent from Brazil who can collaborate with us to solve these problems. Everywhere you have questions: how to dispose, how to do landfilling, how to store the waste, what to do with the unpleasant ambience which gets created, emissions of gases, fire, land availability, because most of these landfills have become a part of the cities nowadays. Earlier, they used to be in the outskirts. How to reclaim the land? If after reclaiming, how would you clean up the land? And so on. So these are the geoenvironmental issues which are related to landfill rehabilitation or landfill reclamation. Recycling can be done of the waste is a big question mark, ruled out. I think people have already ruled it out. Decomposition seems to be a good idea, but the question is, how are you going to decompose it? A lot of research is required in this area. Microbial decomposition is not so easy. Then photo degradation is also not very easy. Then what should be done? Should we adopt thermal degradation, or should we incinerate? Whether it is going to be cost economical and all, these are the questions. So issues to be addressed are both as far as the active working landfills are concerned and the passive landfills are concerned. Passive landfills are the ones who have already lived their life. So as far as the active landfills are concerned, efficiency of the current decomposition method has to be studied. We have to develop mathematical models. We have to understand how much storage capacity can be created. All right, how to scale up the lab results to the real life situations in the field, which are going to be extremely difficult to handle. And of course, how to test and monitor the decomposition of the waste, municipal solid waste in the real life. So everywhere, from starting from collection to sample sizing to storage, there are questions and questions and questions. People need to answer them. Similarly, for the passive landfills, what should we do? Should we biomine them? If you are biomining, the question is, when should I initiate the biomining? Studies have not been done. So we have to live with them. They have become monuments of the modern day society. And even if you mine them, how will you mine them? Where are you going to keep the mine residues? What are you going to do with the mine residues? Are you going to screen it? What technology is to be used? How space will be utilized? After screening, whatever the fractions are getting created, where are you going to use them? So several questions are being asked by the governance. And unfortunately, technologists are not having clear ideas about what to say. And then comes the economic feasibility. Second issue, whatever anthropogenically generated geomaterials are, like municipal solid waste, legacy waste, there are accidents, there are fires, bauxite residues, fly ash is being stored in different storage ponds. And I think this was the best presentation given by Paul a few days back. The failures. Brazil has an excellent understanding of how these failures have occurred. And then they are the ones who can guide us in this area, how to deal with the anthropogenic geomaterials. Breaches in the dams, how to come out of the breaches. See, this type of situation where the dams are becoming very old. So tailings, dams and failures, this is where we need help. And I was really happy to see this type of a news item where the Hydro is a company in the Brazil. They are going for sponsoring research at a mega scale for sustainable use of the bauxite residues. And if you look at the salient features, is the laboratory of microstructure and eco-efficiency. I really appreciate this. And then for creating more sustainable alternatives, uses of bauxite residues. Incidentally, bauxite residues are the waste products which have very high pH values. So the other day when somebody was talking about the accidents which have happened in India, I was the person who was investigating them. It's not a very simple phenomena. When we talk about, highly active contaminated material interacting with the soils and rocks and what happens. Some of you who are aware of zeolitization of the material, this process might be occurring over a period of 30, 40, 50 years, but then these studies have to be taken up. Development of eco-efficient cementitious products. This is where the main theme is, main focus is of the researchers, how to utilize these waste and create eco-efficient cementing materials. And of course, the idea is to market them, to generate new business. And once you generate new business, new employment, new income, promoting development of the region can be done. And then all these industrial byproducts can become resource. That is what I call them as valorization. And also, it will help you in reducing the carbon footprints. So this is the top priority. And this is where I say the long lost twin should collaborate to attain SDGs. This is what actually is happening in India right now. Several researchers are studying thermohydromechanical chemical processes at the laboratory scale, industrial byproducts, sustainable utilization for infrastructure creation, carbon capture, utilization and storage. And this has become a very big agenda where methane gas hydrates are being studied, displacement of methane gas by using carbon dioxide under frozen conditions is being studied. And of course, some efforts are also being done to neutralize the hyperactive industrial byproducts by mineralizing them with the help of carbon dioxide, sulfur trioxide injection. So these studies are being taken up by some of us. I would like to take the opportunity of bringing to your notice the mission mode project which I was talking about. Please visit my website and try to contribute, because I can see that there are many potential collaborators from Brazilian side who can be a part of development of technology roadmaps with actionable recommendations. Technology roadmaps are the ones for the researchers and technologists and the industries. Actionable recommendations are the ones for the governments, policies. So the whole idea is I want to bridge the gap between the practice and the policy. So please visit the site. You will find the mission industrial byproducts, and there is a form which I have included, a Google form. You can feed your information, and then I will contact you. So what are the potential IBPs which we can work together? These are the big list of potential IBPs. All right, bauxite residues, slags, ash from combustion, biomine waste, mine tailings and overburden from mining. These are construction and demolition waste, dead sediments, rubber waste, cold washery residues, agricultural waste. List is never ending. But however, the top priority in which both of us can work is bauxite residues, the mining overburdens, mine tailings, and ash of different types. And of course, the landfills and the unscientifically closed landfills and dumps. So the key considerations is how to create circular economy. Then only the alleviation of the poverty will take place. So this is where the geoenvironmental engineering gets linked with the societal issues. Alleviation of the poverty, promotion of more jobs. And this is what the circular economy would be coming out of the waste material, so-called waste. We have to create technology, and this is where the corporate social responsibility also comes in the picture, and we should be working on these issues. At last, the whole idea is that once we collaborate together, sustainable development initiatives can be taken care of. This would be another top priority of the twins, which I have been talking about. I have also launched a Geo-Environmental Research and Innovation Center, and those of you who are interested can visit to this site, www.iscg.info, and this is where you will find, I call this as a SEGRIN, and this is the virtual center for Geo-Environmental Research and Innovation. And this is again the third priority where we can collaborate and work together. So thank you very much. I hope that the long last twins will collaborate and champion the sustainable development through adequate practice of geoenvironmental engineering. Thank you very much for giving me this opportunity. And I must thank my younger colleagues, especially Fakhra Rashid, Kamran Ilahi, and Harshvardhan Meena, who have helped me in coming out with this presentation. Thank you very much.
Thank you. Thank you, Professor D.M. Singh, for an excellent presentation where you really, tried to show how India and Brazil can interact. It was a beautiful presentation wherein, you stressed on long lost twins and mentioned the areas where we have a lot of commonalities. And then, you took us to sustainability and then the areas in which we can work together. I wish your dreams and the dreams of the two geotechnical societies come true very soon. Thank you very much.
Thank you. Welcome, Professor Enio.
So, Professor Negro, yeah, you can take over now.
Yes, thank you. Well, thank you, Dr. Thank you, Dr. Singh, for the long lost twins. Very inspired and truthful parallel between the two countries, and that to a large extent justify the initiative the Indian and the Brazilian Geotechnical Societies are taking and are taking ahead. It's very clear from your presentation how much in common and how much we have to do, and how much could be our resource, our efforts, how productive they can be. Thank you so much.
Thank you very much.
And our next and final speaker, we will deal with some part of what Dr. Singh mentioned, is Professor Enio Palmeira from University of Brasilia. Enio is a professor of civil engineering in Brasilia. He obtained his BSc degree in civil engineering from the Federal University of Rio de Janeiro. And also he got his Master of Science degree at the University of Rio de Janeiro. And his PhD was taken from the University of Oxford in the United Kingdom. Professor Palmeira is a member of the Brazilian Academy of Science and a honorary member of the International Geosynthetic Society, IGS, likewise our Indian Geotechnical Society. He received the IGS award in 2 occasions from the IGS, the Scientific Merit Award from the Brazilian presidency and the José Machado, and also the Tazagi Award from the Brazilian Geotechnical Society. He is editor of the journal Geosynthetic International, associate editor of Geotextile and Geomembranes, and of the Canadian Geotechnical Journal, and member of the editorial board of the International Journal of Geosynthetics and Ground Engineering, Environmental Geotechnics and Soils and Rocks, the journal of the Brazilian Geotechnical Society. He carried out research on geosynthetics for 42 years and has received many national and international awards. His topic is going to be geosynthetics and alternative materials for sustainable geotechnical and geoenvironmental solutions, quite in line to what we have just seen through Dr. Singh's presentation. Professor Palmeira, can you go ahead now, please?
Let me share my presentation. I wonder if you can see it.
Yeah, it's quite clear.
Okay. Thank you, Mr. Chairman, for the kind introduction. I would like first to thank the organizing committee of the webinar for inviting me for this presentation, and also to congratulate the Brazilian and the Indian Geotechnical Societies for this excellent webinar. So the title of my presentation is Geosynthetics and Alternative Materials for Sustainable and Sustainable Geotechnical and Geoenvironmental Solutions. So this slide shows the contents of the presentation. We will start with a brief introduction, and I will show you some examples of sustainability of works with geosynthetics, some geosynthetics applications as reinforcement of marginal and alternative soils, like in paved roads with marginal fill materials, the use of mining waste as a sub-ballast material in a railway, retaining walls built with recycled construction demolition residues as backfills, and the use of recycled construction demolition residues in geotextile encased columns. I also show some examples of geosynthetics and alternative materials in some geoenvironmental application, and I will finish the presentation with some final remarks. So let's start with the introduction. Geosynthetics have been used in several geotechnical and geoenvironmental works, and as drainage, in separation, when one wants to separate a good quality fill material from a poor quality subgrade, as filters, as barriers when we want to protect a soil from a pollutant, as reinforcement when we want to reinforce a soil mass, and also in protection when we want to protect the ground, for instance, in erosion control works. So let's see some examples of the sustainability of works with geosynthetics and conventional construction materials or conventional soils. Stuck and co-authors, they developed a research comparing 2 filter systems in a pavement of a highway. The reference section studied consisted of a pavement with a granular filter, a sand filter, and the alternative geosynthetic solution, the filter was a non-woven geotextile. So in both cases, the soils and the dimensions were the same. The only difference between these 2 sections was the filter system. And they evaluated the reduction in some environmental impact parameters due to the use of the geotextile filter instead of the sand filter. So the parameters that they investigated were acidification, eutrophication, gases that contribute to global warming, non-renewable energy consumption, renewable energy consumption, and water consumption. So this figure shows the reductions caused by the use of the geotextile filter, where you can see that in most of the cases, the reduction of these environmental impact parameters are over 90% and almost 100% for the water consumption. Another example that they investigated was by comparing two retaining structures. The one on the left is a conventional gravity concrete retaining wall, and the one on the right is a geosynthetic reinforced wall. Both walls with the same height, same soils, and same overall conditions in the two cases. So this figure shows the reductions in the environmental impact parameters when one chooses the geosynthetic reinforced wall. Again, in most of the cases, reductions over 70% with regards to gases that contribute to global warming. The solution with the geosynthetic reinforcement reduced its emission by approximately 81%. Another example involving retaining walls. Here, Daniels and co-authors studied or compared some environmental impacts for three retaining structures: a conventional gravity wall made of concrete, a cantilever wall, and a geosynthetic reinforced wall. So this figure shows the amount of CO2 emissions as a function of the wall height. Again, all the soils and dimensions are the same, or heights are the same. And you can see here that for the geosynthetic reinforced wall, the amount of emission of CO2 is much smaller than those from the conventional retaining structures. The figure on the right shows the consumption of energy, and again, the consumption of energy for the geosynthetic reinforced wall is much smaller than those for the concrete gravity wall and the cantilever wall. So geosynthetics can provide sustainable solutions when we use conventional materials or conventional soils. So we would expect they would be even better for the environment if we combine them with marginal or alternative materials, alternative soils. So let's see some examples of that. In this study, Ribeiro and co-authors investigated 5 solutions for a base layer of a pavement and a highway. The conventional solution, the one which they use commonly in the region, is a mixture of fine soil, local fine soil, with crushed rock, and 1 part of fine soil for 4 parts of crushed rock. So this is the reference experimental section. The other sections, one of them is the same fine soil, but improved with 2% of lime. The other section here is just a fine soil with a geotextile below the asphalt cap. In this other section is the fine soil with the geotextile layer at the base of the pavement. And in this last experimental section, the fine soil was enveloped by a non-woven geotextile impregnated with asphalt. The objective here was to try to keep the moisture content of the fine soil as constant as possible. So here you see some images of this research, the installation of the geotextile in the field in one of the experimental sections. Here on the right, the impregnation of the geotextile with asphalt, and field and laboratory tests were carried out as part of the research program. So this table lists the main properties of the subgrade in the region in terms of Atterberg limits, percentages of fines in the soil, TRB classification, A75, a unified soil classification system, MH, and the California bearing ratio of the soil obtained in laboratory tests on inundated samples was equal to 17%. Here, the properties of the soils used as base materials, the properties of the fine soil in terms of Atterberg limits and grain size distribution, the soil lime mixture, and the soil crushed rock mixture, and again, the TRB classification and USCS classification. The properties of the base soil, additional properties in terms of maximum dry unit weight, optimal moisture content, swelling, and California barren ratio, where you can see that the California barren ratio of the fine soil is significantly smaller than the values for the soil lime and soil crushed rock mixtures. Let's see some results. First, in terms of field plate load tests to obtain the base soil reaction modulus under vertical stress of 560 kPa. So here you see the results in terms of base reaction modulus for the different experimental sections investigated. And you can see that the results obtained with the combination of just the fine soil and the geotextiles were comparable, or in some cases even greater than those of the conventional or the standard or reference section or the conventional solution, both at the end of construction and after 4 years in service of the highway. Here results of pencil pressure meter tests on the base layer. Here you won't see the result for the fine soil crushed rock mixture because the soil could damage the pressure meter. So here we have only the conventional mixture of fine soil and lime. And again, at the end of construction or after 4 years in service, see the results with just the use of the fine soil and the geotextile provide a very good results, showing similar results as those of the fine soil and lime mixture. Results from Bankman and beam tests on the base soil modulus for the different experimental sections, and again at the end of construction and after 4 years in service, again similar results as those of the reference section and of the fine soil and lime mixture with the use of the fine soil and the geotextile. Additional Bankman beam test in terms of deflection along the distance. The red curve here is the result for the soil crushed rock base layer, and the blue line for the geotextile enveloping the fine soil, and the similar results. And after 4 years in service, the results for the section are very, very similar, showing again the good performance of the sections with the geotextile and just the fine soil, which certainly provides savings in the construction of this type of highway. Another study regarding the use of the combination of alternative materials and geosynthetics was carried out by Fernandez and co-authors in the Victoria Minas Railway, which is an approximately 800 kilometers railway in Brazil, a very important railway that transports mining products, a very busy one. So in this figure, you see the typical cross-section of the railway and of the experimental sections that were investigated. And the objective of this research was to study the possibility of using an alternative subballast material instead of the conventional and more expensive subballast material commonly used in this railway. So the soils involved in this study, the alternative subballast material was a mixture of 50% of a local soil or silty sand, plus 25% of a fine mining waste, a sandy silt, plus 25% of the conventional subballast material commonly used, a sand gravel. And the subgrade soil was a silty clay sand with a California barren ratio of 67% and a Young modulus after surface compaction of 100 megapascals. The reinforcement used was a geogrid with 30 by 30 millimeters apertures, made of polyester fibers with a PVC cover, with tensile strength of 65 kilonewtons per meter and a maximum tensile strain of 10%, and a tensile stiffness at 5% strain of 520 kilonewtons per meter. You see a view of one of the experimental sections with the type of vehicles that passed on the railway doing a bankament beam test. Another views of the experiment, here a view of the track of the railway, the installation of soil strain gauge to measure strains in the subballast layer. And again, the same photo as before, showing the locomotive with the wagons, with an equipment with 8 axles and 1600 kilonewtons total weight. It's important to point out that the same traffic of trains that passed on the real railway was the traffic that passed on the experimental section. So the same type of train, the same loading, and the same traffic intensity. So here's some results in terms of grain size distribution curves of the materials involved in this study. The blue curve is the grain size distribution for the ballast layer. The black curve is the results for the conventional subballast material, and the red curve is the grain size distribution for the alternative subballast material. So you can see here that the alternative subballast material is considerably finer than the conventional subballast used in the railway, commonly used there. This figure shows a typical cross-section of the experimental sections. Section S1 is a reference section built with the conventional subballast material. Sections S2 and S3 were built with the alternative subballast material, reinforced with geogrid at the base of the subballast layer or at the top of the subballast layer. And section S6 is a section with just the alternative subballast material without reinforcement. For comparison, just to check how this alternative material would behave without the presence of reinforcement. Here results of bankament beam tests carried out in terms of deflection along distance. The red curve here is the result for the reference section, S1, and the blue and green curves are results for the sections with the alternative subballast material reinforced with geogrid, and you can see very similar results. And as expected, the worst performance was the one from the section S6 with just the alternative subballast material, showing that the presence of the reinforced made a significant effect on improving the performance of the alternative subballast. Now, in terms of strains in the subballast, horizontal strains versus the number of axles passing on the experimental sections. You see the red curve is the result for the reference section with the conventional subballast, showing larger strains than those measured in section S3 with the alternative subballast reinforced with geogrid. And again, the worst performance observed in the section with just the alternative subballast material. An additional benefit brought by the presence of the reinforcement is the reduction of ballast particle breakage. So this figure shows the percentage of ballast particles that were broken during the time of monitoring, or as a function of the number of axles, where the red curve here shows the results for the reference section, which was the section with the largest breakage, followed by the section with just the alternative subballast material and smaller breakage levels for the reinforced alternative subballast material. So this is an additional benefit because it brings savings to the maintenance work of the railway. Another combination of geosynthetic reinforcement and alternative construction materials was studied by Santos and co-authors. They built 2 experimental retaining walls, geosynthetic retaining walls, 3.6 meter high, with spacing between reinforcements equal to 0.6 meter. And these walls were built on the porous collapsible soil, very common soil in the city of Brasileira, where this research was conducted. And the walls were instrumented with strain gauges, horizontal stress cells, vertical stress cells, and in kilometers at the wall's top. And the novelty of this research was the use of construction demolition residues as backfill material for the walls. So this photo shows a bird's-eye view of the walls at the end of construction. Wall 1 reinforced with geogrid, and wall 2 on this side reinforced with a non-woven geotextile. Another views of the walls, the face of wall 1 at the end of construction and the face of wall 2 reinforced with geotextile. And you should note the greater bulging at the face of the reinforced wall, the geotextile reinforced wall, due to the smaller tensile stiffness of the non-woven geotextile under no confinement or under low confinement. Because the walls were built on a collapsible soil, it was also interesting to investigate the effect of the foundation soil collapse caused by inundation. So pools were constructed, and at the base of the walls there was a drainage layer, so the water could infiltrate in the foundation soil to enhance the collapse of this unsaturated soil, or to add to previous collapse caused during the rainy period in the region. This table shows the properties of some materials, the recycled construction demolition residue in terms of grain size distribution, unit weight, friction angle of 41 degrees, cohesion of 6 kPa, and the geosynthetics that were used as reinforcement. Geogrid 1 was a polyester product with 20 by 20 millimeters apertures, a tensile strength of 20 kilonewtons, a second tensile stiffness at 5% strain of 300 kilonewtons per meter, and a strength break of 12%. The non-woven reinforcement used was a non-woven geotextile used in wall 2, was a polypropylene product with a tensile strength of 24 kilonewtons per meter, a second tensile stiffness obtained in isolation of 15 kilonewtons per meter, but we know that when the geotextile, non-woven geotextile, is confined by soil, its tensile stiffness can increase significantly, and in this case, can vary between 160 and 280 kilonewtons per meter, being 280 very close to the geogrid tensile stiffness, and a strength break of 70%. The instrumentation consisted of strain gauges to measure geogrid strains, telltales to measure strains in the geotextile, total stress cells to measure vertical and horizontal stresses in kilometers at the wall top, and wall face displacement and wall settlements were also measured during the experiments. And this image shows the instrumentation and installation of some instruments in the field. Let's see some results. First, in terms of settlements along the wall top, 1 year after construction. Here, the settlements are normalized by the wall height. So you can see here the settlement profile for wall 2, a very uniform settlement profile for the wall reinforced with geotextile, and a not so uniform settlement profile for wall 1. And the reason for that was that the soil below wall 1 was more collapsible than the soil below wall 2. So this explains this difference between results. And the settlements after foundation soil collapse caused by inundation, and you can see here there is a significant increase in the settlements, but wall 2 is still maintaining a very uniform distribution of settlements, and not so uniform and larger settlements for wall 1 because of the reasons mentioned before. Tensile strain in one of the layers that was instrumented, layer 3, which is this layer here, the strains along the reinforcement length in wall 1 before and after foundation inundation, very similar results, showing that the inundation of the foundation did not affect significantly the strains in the reinforcement. The same thing for wall 2, before and after inundation. but you should see here that the strains close to the wall face in wall 2 are significantly higher than those in wall 1 because of the smaller tensile stiffness of the non-moving geotextile without the presence of confinement. But if we enter a bit, about 30, 40 centimeters inside the reinforced mass, then the tensile stiffness of the geotextile increases and the strains are very, very small, comparable to those measured in wall 1. Now wall face horizontal displacements before and after subgrade inundation for wall 1. You can see here before and after. The horizontal displacement is normalized by the height of the wall 2 here in this case, and some increase in the horizontal displacement due to inundation in wall 1, the same thing in wall 2, with larger horizontal displacement if you consider the displacement at the face of the wall because of the influence of that bulging at the face. But if you measure the displacement a bit inside the reinforced mass, then the displacements are smaller and very similar to those measured in wall 1. Foundation soil horizontal displacement 1 year after construction. You see here the profile horizontal displacement for wall 1 and wall 2. Similar results with similar values of maximum horizontal displacement. And after inundation of the foundation soil, there is a significant increase here, about 30% increase in the maximum horizontal displacement of the foundation soil. But again, a similar overall distribution of the displacements with depth. Well, another combination of recycled construction and demolition residues can be made regarding the use of granular columns or geotextile-based granular columns. Granular columns have been used as a conventional solution to stabilize embankments on soft soils, but it has a limitation which is related to the bulging that can occur at the top of the column because of the weight of the embankment that is transferred to the column. So this bulging will reduce the efficiency of the system in reducing the embankment settlements. So the use of a geotextile encasement can minimize or reduce this bulging and then increase the efficiency of the solution. So a large model scale test was carried out in our laboratory, involved the tests on conventional and geotextile encased granular columns, and the equipment could contain a very soft soil with instruments such as pressure cells and power pressure transducers, and the column was loaded at the top by a loading platform. So the properties of the geotextiles used as encasement are listed in this table. 3 geotextiles were tested with tensile strengths varying between 8 and 30 kilonewtons per meter, maximum tensile strength between 15 and 22%, and stiffness at 5%, strain tensile stiffnesses between 53 and 120 kilonewtons per meter. The soils involved in this study, this table presents the main properties of the 3 infill materials that were used: a sand, a gravel, and recycled construction demolition residues. You see properties in terms of grain size distribution, and very similar friction angles for the 3 materials, and very similar dilation angles as well. This other table shows the properties of the soft soil. The main properties: a very soft soil with a undrained shear strength obtained from vein tests around 5 kPa. And this figure shows the grain size distribution of the materials. The red curve is the distribution for the soft soil, the brown curve for the sand, and the green and the blue curves are the grain size distribution for the gravel and for the recycled construction demolition residues. This was intentional. The idea was to test gravel and RCDR on the same basis regarding the grain size distribution. So let's see some results here. Results of load test in terms of settlements. versus load. And you can see here that results were very similar for the three infill materials, showing the potential of the use of recycled construction demolition residues as an infill material for geotextile encased granular columns. Additional results in terms of load capacity here for tests on conventional columns without geotextile encasement and geotextile encased columns. And you see here that this scale is a log scale because the results for the conventional columns were much smaller than those for the geotextile encased columns. And you see also that the performance of the RCDR as an infill material was very good when compared with conventional materials commonly used as infill of geotextile encased granular columns. So let's see now some examples of combinations of geosynthetics and wasted material in some geoenvironmental applications. Well, some materials that are disposed in nature or in landfills can cause environmental problems like plastic bottles or plastic objects in general, and also wasted tires. In the case of wasted tire, they can, besides cause environmental damage, they can also become public health hazard. And when a pile of wasted tires catches fire, it is a type of fire very difficult to be extinguished, and there's an obvious air pollution, important air pollution in the region. So the alternative construction materials that we will consider here in these presentations are recycled construction demolition residues, PET bottles, entire or compressed PET bottles, wasted tires in the form of chips or grains of wasted tires, or whole wasted tires. So this image shows examples of this type of combination. Here, a drainage system of a landfill combining whole tires and a geotextile filter. And in this photograph at the bottom, a drainage trench and a highway combined wasted tires, chips, and a geotextile filter. And in this drainage trench here, the combination of a geotextile filter and compressed PET bottles. So this type of solution can be cost-effective when natural materials, granular materials, are scarce or very expensive. So here another combination of PET bottles, in this case, the entire PET bottles, to build infiltration trenches to minimize floods in urban areas. The geotextile filter and the PET bottles, and the idea here is the trench to capture the runoff water or the water from rain, and to help infiltrating this water in the foundation soil in a way to reduce or avoid floods in urban areas. Another combination regarding drainage system was investigated by Junqueira and co-authors. They tested two municipal solid waste experimental cells, and in the reference experimental cell, the drainage system consisted of a gravel layer with a drainage trench at the middle, also filled with gravel, about 50% of municipal solid waste, and the waste was instrumented with settlement plates and temperature gauges, and the figure shows the general dimensions of this cell. The alternative drainage system tested consisted of a combination of whole tires and geotextile filter at the base of the waste, geomembrane in both of the cells, and the central drainage trench filled with tire chips, same dimensions as the reference experimental section, the same amount and same type of waste. And this photograph shows an image of this waste cell during, during construction. Well, this result shows variation leachate effluent volume versus time for both cells. The red curve is the result for the conventional drainage system with the gravel layer. And the blue line is the result for the alternative drainage system. And pretty much the same results showing the good performance of the alternative drainage system in the experimental cell. And these rather horizontal segments here are dry seasons in the region, which what we are passing now, the reason why my throat being quite dry at this moment. The other result is the result of variation of suspended solids with time, showing that the amount of suspended solids coming from the alternative drainage system was significantly less than those from the conventional drainage system. And too much suspended solids in the leachate can cause clogging of drainage pipes and drainage systems in landfills. Another combination of alternative wastes, alternative materials and geosynthetics can be made to produce alternative geocomposites. So let's see some examples regarding alternative geocomposites for drainage. Here on the left, you see some images of conventional geocomposites consisting of a geotextile filter with a drainage core of a geonet or a geospacer. And here's some possible alternative geocomposites for drainage. Here, a combination of geotextile filter and plastic bottle caps to form the drainage core in between geotextile layers. And here, geotextile filter combined with wasted tire strips to form the drainage core. So let's see some results in terms of in-plane discharge capacity obtained from a test, transmissivity test. Here, this image shows the equipment of transmissivity tests for tests under pressure. And the figure on the left shows results of discharge capacity versus vertical stress for two conventional geocomposites found in the market, where you can see that for stresses over 200 kPa, there is a reduction in the discharge capacity caused by the compression of the drainage core of this product. The figure on the middle is the result for the alternative geocomposites made with PET bottle caps, and similar results as those of the conventional geocomposites for stresses under 100 kPa. And as you increase the spacing between caps, you increase the compressibility of the geocomposite, and this will affect the discharge capacity of the composite. The figure on the right shows the discharge capacity versus vertical stress for the geocomposites manufactured with wasted tire strips. And again, very similar results as those of the conventional products for stresses under 100 kPa. And again, as you increase the spacing between strips, you make the product more compressible and more influenced by the vertical stress. So this is the type of product that can be assembled or manufactured in the landfill plant, because we are usually plenty of wasted tires or plastic bottles present in the landfill. Another combination can be made regarding geocomposite clay liners. In this figure on the left, you see a typical cross-section of one type of geocomposite clay liner, GCL, consisting of a layer of bentonite with a top and bottom layers of geotextile. And what we can think of is an alternative geocomposite clay liner consisting of a bentonite mixed with some alternative material, and also with a geotextile at the top and bottom. But this mixture brings some concerns. For instance, the expansibility reduction, possible permittivity increase, and the mixture can also cause increase in manufacturing costs or difficulties in manufacturing. So this has to be kept in mind too. So here's some results in terms of permittivity and expansibility tests, the type of equipment used in some of these tests. The figure on the left shows the variation permittivity with normal stress, the red curve being the result for just the bentonite, and the other curves, the results for mixture of bentonite and different percentage in mass of rubber. You can see here a significant increase in permittivity, although the permittivity in this range is still very small, but there was an increase in permittivity. And when we think of alternative GCL with the mixture of materials and bentonite and geotextiles, this result shows the variation of expansion with time of the geocomposite. The two red curves are results for conventional geocomposite products found in the market, and the other curves are results for geocomposites with mixtures of bentonite and 50% in mass of rubber, or 50% of a kaolinitic clay, or 50% of sand. So you show some, here you see some results, some reduction of expansion, but alternative geocomposite is still expanding to some extent. And so this type of concept could be applied as an additional barrier system in a landfill, particularly in less important landfills. So I finish my presentation with some final remarks. Geosynthetics can provide sustainable engineering solutions when used with conventional soils. This has been shown in several works in the literature. Waste and marginal soils may be used associated with geosynthetics, particularly if the waste and marginal soils have good mechanical properties. And the feasibility of using marginal and waste materials increase the sustainability potential of geosynthetics applications. Combinations of geosynthetic and recycled construction, demolition residues, and mining wastes are particularly interesting, but we have to keep in mind some concerns regarding the possible variations of properties of these mixtures or these combinations, and also competition with other industries. For instance, the recycling industry and the construction industry also demand for wastes, and we certainly need a great amount of waste or alternative materials in geotechnical engineering works. So I'd like to acknowledge some contribution, particularly from several research students. We helped with their research. I present part of them here. The sponsoring agencies that have supported our research activities, geosynthetic manufacturers also for their support, and the India and the Brazilian Geotechnical Societies for the invitation for this webinar. Thank you very much for your attention.
Thank you very much, Professor Enio Palmeira, for your quite creative presentation of alternative materials combined with geosynthetics with great positive impact for the environment and for society. Contribution very much aligned with sustainable governance of infrastructure projects. Thank you. I think we have still a bit of time for some discussions. I wonder if Dr. Prasad can bring anything. I have two questions listed here.
Oh, really interesting. Here, from my side, I do not see any question, maybe because people may feel that, we have encroached their lunch time in Brazil and supper time in India. So I don't have any question here. Please go ahead with the questions, Professor Negro.
They are relatively simple questions by the fact they are very complex, as a matter of fact. One to Professor Singh. Could you comment on contributions from environmental geotechnics to minimize the hazards brought by the COVID-19 pandemics? Could you make any comment or any thing that really contributed for that function, please?
So, Professor Negro, you must have noticed in my presentation, I have specifically mentioned about the 5 papers which are dealing with past, present, and future of the pandemic-like situation, how the education system should be changed, adopted. Number 2 is what is the impact of COVID type of situation, pathogenic activity in particular, migrating to the geo environment, water bodies. This is a major issue. How to safeguard water bodies. Number 3 is how to manage the municipal solid waste itself, because everything is getting mixed up. 4th issue is the plastic waste, which is going into the municipal solid waste and which turns out to be ultimately microplastic, MPs we call them, or nanoplastic. And both MPs and NPs have become a nuisance because ultimately they become a part of the food chain. And the 5th paper which we have written is more of a guideline that how to dispose, how to bury the dead bodies which were infected by COVID-19 type of a situation in a very respectful manner, in a very scientific manner. So these are the papers, I think, which are going to be a solution for the tomorrow. People will be better prepared, guidelines will be created, a lot of research would be done, particularly in the field of how pathogen and virus migrates in the porous media. And that's opening up a very new subject in the realm of geotechnical engineering. It's becoming big and big and big.
Yeah, yes, indeed. Yes, indeed. Thank you. And I have a final question to Professor Enio. Carbon footprint seems to be a quite inherently inaccurate index. But the carbon print of using geotextile is so much smaller than traditional geotechnical solutions that I wonder how come for a product of a high footprint such as the plastic industry, and perhaps for being solutions involving slender elements or smaller volumes of materials, can you bring up some explanation for this?
Yeah, several researchers have investigated that in the last, particularly the last 20 years. And their computations have shown that, at least in the case that they analyzed, the contribution from the geosynthetic solution, they can provide much environmentally friendly solutions than conventional ones. And this, all things considered, when you think, for instance, of course, if you think of just a filter layer, then the contribution may be small in terms of the environmental impact of the entire project. But if you think, for instance, in a reinforced wall or retaining wall, you have impacts when you use the geosynthetic reinforcements, which are much smaller because, for instance, to build a concrete wall, you have to have cement, you have to have gravel, you have to have sand, you have to have water, and all this material have to be transported with trucks to the site, and this consumes energy and emits gases to the atmosphere. And when you have the reinforced soil, you save a lot of these factors that would impact the environment. So I believe that this large difference between the two, this type of comparison, is due to this type of conditions. You use less material, you transport less material, the installation and the construction is quicker than conventional solutions. So I believe that's the main reason for this less environmental impacts of solutions using geosynthetics.
A final question came just now. PET bottles filled, I'm reading from the chat. PET bottles filled with any material or empty bottle, please clarify, sir, is to Dr. Enio Palmeira.
Yes, the examples that I presented are empty bottles. They can be used the entire bottle, like in that drainage trench to infiltrate water in the ground, or as a compressed bottles being compressed to form what would be a large size element in a drainage layer. We have used this kind of solution in Brasilia, the city where I live, the compressed PET bottles, because gravel here is very expensive, and we have sources of gravel around the city, but they are in regions that are environmentally protected. So some engineers have used compressed PET bottles as drainage layers in some works. But again, it's usually you need a large amount of PET bottles. So you have to have some kind of industry to provide this kind of material to be able to use in a typical geotechnical environmental project.
Well, circular economy will facilitate you finding, I mean, the resource, the waste you need for your project. That's the idea. Perhaps Dr. Prasad could have a few words before I close the session and the webinar, please.
Okay. Thank you, Professor Negro. I think we had two excellent lectures, very well planned and very well presented. So thanks to both Professor Singh and Professor Palmelo. This is the beginning of the interaction between the two great geotechnical societies, and we shall continue to have, many more with the best brains from both these geotechnical societies taking our journey forward. And I thought, the visionary from Indian geotechnical side, Professor Shivkumar Babu, should have the last word from our side. So I will request Professor Shivkumar Babu to, quickly give his message. Before signing off, I would like to say that I belong to the southern city in India called Mysore, a very, very good cultural tourist city, very similar to the southern city in Brazil, Curitiba, where also a lot of culture is there. And these two cities, I believe, have a lot of works done towards sustainability. So I invite all our Brazilian friends to India and to my city. And of course, after this pandemic, in which, both of us have suffered quite a lot. So before I will sign off, from now, mentioning that I had an excellent time during these 3 days, and I request Professor Shivkumar Babu to take over.
Thank you, Professor Prasad. It has been 3 days of interesting lectures filled with a lot of information, a lot of love towards each other. I think it is something very great. I think we started on a very good note, and we had excellent speakers from both the sides trying to cover the spectrum of areas. And in fact, Professor D.N. Singh could give from DST side some ideas on how can we go forward. And I think this is just the beginning. And I would like to thank all of you for a very, very, interesting and enthusiastic participation. I've been in touch with the president of the Geotechnical Society from Brazil side. We have excellent online meetings and all that, and even the excellent participation from both the countries, the participants. So I would like to thank you all from the Indian Geotechnical Society, and I assure you that we'll continue to have this cooperation, because there are a lot of common things that we can do together. Thank you very much. Thank you from all the best from our Indian Geotechnical Society side. Thank you.
Perhaps Professor Fernando Schneid might have a final word before we close the session between the two long-lost twin countries that has been proved very productive and very interesting. And that's the basis for innovation. I mean, to sum up effort and being creative. Fernando, are you there?
Yes, I'm here. Yes. Just mention that I share the views from Professor Babu I share your views, Arsenio, about this 3 days webinar, which is getting to an end now. And I understand from my perspective that we have achieved all the expected goals in promoting experience exchange between the professionals of our two countries. I think that I personally judge an event by how much I learned from it. And I have benefited a lot from what I've seen in these past 3 days. Our professionals covering technical and scientific issues, showing what the state of practice is in our countries, introducing examples of the state of the art. And we have learned that to use the same international codes and regulations following international standards. It also becomes clear that we have the same challenges. The challenges in providing adequate infrastructure in terms of transportation systems, ports, power, water supply facilities to promote economic growth and improve the quality of life. So I think that this was also all put into perspective throughout these days. And most importantly, I think the essential point is that we have the human resources for going through these challenges. And this was demonstrated by the remarkable contributions from our colleagues throughout these 3 days. So as a closing remark, I would like to take the opportunity to thanks for all those that have contributed to organize this webinar. Professor Simadhaya, Professor Babu, Dr. Nilima, and by mentioning these names, I extend to all our colleagues from the Indian society. Thanks very much for the opportunity. I see this webinar as the first stage towards a more close cooperation between our countries. And so I hand it back to you, Arsenio, for closing the session.
Well, thank you for the final words, Fernando. I think that I don't have anything more to add, but just to keep in mind the very happy expression Dr. Singh mentioned of the Long Lost Twins Association. Thank you very much for this parallel, and I declare close our first webinar.
Thank you.
Good.
Thank you.
Thank you, everybody. All the best for everybody.
Excuse me, before we sign off,
Okay,
I'm
Professor.
NK Samadhya.
Oh,
Sorry,
yeah.
I could not attend all the sessions today, but I would like to thank both the IT teams, IT team from Brazil and our Mr. Nitin Tiwari.
Dr. Nitin Tiwari.
He will be doctor maybe after about 3 months or so. He has already submitted his PhD. So for all the technical support, both the teams have given. So I would like to mention that they have done a great job because there was no technical problem in all the 3 days. So besides thanking all the speakers, I think we should also thank both the IT teams.
Yeah.
And especially Dr. Professor Nilima Satyam. She was instrumental behind this, and Professor Babu. Thank you so much, and we will have cooperation from both the societies and near future also. So we will have another program, maybe this year or maybe next year. So thank you so much, and have a great day today in Brazil side, and good night to all the Indian friends. Thank you so much.
Thank you.
Thank you.
Thanks a lot. Thanks a lot, and take care, please.
Thank you, Professor Samadhya.
All the
Bye-bye.
best. Bye now.
Bye.
Thank you, Singh Saab.
Bye.
So with your permission, shall I close this?
Yeah, close. Go ahead. Yes.
Okay.
Close.
Okay.
Thank you.
Thank you.
Thank you,
Thank you.
Nitin. Thank you, Nitin. Thank you.
Thank you, sir. Thank you. Thank you, sir.